how do I say, my ardent desire to be trying to explore or to share this kind of field to a larger group of people, and then we can, of course, learn together. So I would like to share to you, to everybody, things that I've learned, and then maybe we could have some discussions, maybe after the meeting, or you can send me a message or email me later on if you'd be interested. Okay, so but unfortunately, for the interest of bandwidth, I have to shut off my camera. It's not that I'm shaking already, but my internet is a little bit shaking. So thank you again for the committee, and congratulations for this. I'll try my best to make it very, very informative. As I mentioned, this is actually my mission to really tell everybody about microelectronics. So good afternoon. So I begin to share my slide for a moment. There, for a while. Okay. Great. So good afternoon. I just want to confirm if you are all seeing my slide.
Yes, sir.
Okay, so we have around 200 slides here. So, but definitely I'll just tell you the important aspects, things that you need to remember, and on the aspect of how to design this, and what will be the best practice to do so, and so on and so forth. So thank you again. And to begin with, you can call me Sir Mikey. I'm affiliated with the University of Santo Tomas in the Department of Electronics Engineering. My major, again, is more microelectronic engineering. And to begin with, why is it going to be necessary? Because there are a lot of industries nowadays that focus on either developing the technology. So later on, I'll be revealing to each and everyone what does it mean to say technology, and also those that design integrated circuits. It's like saying that there's quite a growing group of people or industries that build chips that they say run the world. And in Philippines, there are about 6 industries now. I have listed some of them here. And it's going to be growing to 12. And so there's something like an explosion of opportunities specifically for microelectronics engineers. Okay, so these are but some of the companies you can take a look at later on. They focus on developing the transistor technology, like the ones in Taiwan, like TSMC and UMC, and the one in China, SMIC. And some of those work on developing the design of the integrated circuits. So for today's session, I would love to walk you through the what it is meant to say technology, and we shall try to look at some basic analog building blocks and some digital building blocks. Hopefully, you will have a lot of takeaway today, and that's actually my hope. Thank you so much. I'm actually very excited to hear that there are students here, and very much delighted to share whatever I know. So moving forward, okay, so there's but a lot of revenue, and this shows us who leads the pack on the semiconductor company. It's mainly Samsung, but quite a lot of players on this end sharing the revenues for semiconductors. Now, well, if we try to buy a component in an electronics store and then try to melt or try to remove the protective shield or the cover, you will see something like this. And you can refer to this as the integrated circuit chip. So if you're asking, how big is this? It depends. Sometimes it is just around 5 by 5 square millimeters with components that vary. May it be transistor, may it be diodes, may it be passive components like resistors, inductors, and capacitors. And also some components that allow you to make digital blocks for, let's say, logic gates, or memory elements, amplifiers, and so on and so forth. So this is a very powerful chip, and it's heavily integrated, very high dense, over a very small area. So moving forward, making the chips that run the world. So actually, everything begins on the sand. That is why perhaps you have heard something about Silicon Valley. That is somewhere in the US. And they collect sand to get raw materials to build the chips. Moving on with this. Okay, so a walk to remember the transistor story. Everything began with vacuum tubes. If I remember, the vacuum tube we are referring to is the Fleming valve. But that is more of a diode. But when they added a grid to the Fleming valve, they create the Odeon tube, which is the forefront of transistors. But in 1947, a group of 3 people who later won the Nobel Award developed the first point contact transistor. And you can see it here, displayed here. Sometimes they will call it the cat whisker transistor. And then not so long after, actually this is more of bipolar, this first point contact transistor. These people you see below are Shockley, Bardeen, and Brattain. And then later on, around a decade later, you built the first field effect transistor. And there are actually 2 variants of this field effect transistor, one that uses junction and the other that uses an isolation, or you can say it is insulated gate. So, and then later on, okay, so we built the fundamental component, and what we do is integrate several of these components together. So the very first integrated circuit was built by TI in 1958. You can see on the left, it consists of 1 transistor and 1 capacitor and 2 resistors. The size is about half-inch width. And in 1965, they built a more dense or a denser chip, which consists of 3 transistors, 5 resistors, and over a smaller area. Then around 2 decades or 3 decades later, you built a component the size of a $0.25 consisting of 35 billion transistors. So you might be wondering, what led for us to achieve this much integration? Or when I say integration, what is a driving force whereas we're able to put a lot of these components called transistors on a very, very small package? And you will hear of that later on. So that is a walk to remember on transistors. We started with the vacuum tube transistor. Then we go to solid state, from bipolar junction to field effect transistors. And now we'll talk about more of the special type of field effect transistor, which we call MOSFET. Okay, so it would be nice and good to see the processing technologies. So when you say processing technologies, well, it depends, okay? So if I'm trying to build a chip, what technology should I be using? Should I be using something like bipolar transistor, bipolar and then MOSFET, or mainly bipolar, or the other one that is fairly emerging, which you call gallium arsenide? Or should I use silicon and insulator? But mainstream is using something called CMOS. CMOS would stand for, again, complementary metal oxide semiconductor field effect transistor. I will reveal in a short while what does it mean to say complementary and what is the structure. So maybe I'm gonna give a refresher on what is the structure of an MOS. Okay, so moving forward, so now I actually showed you that there is such a big market for semiconductors. Nowadays, it is really growing. As I mentioned, there are about 6 industries now based in Philippines, and it's going to be 12, I think, in a span of 5 years. And in other countries, especially, for example, the heart of Asia or Taiwan, this is the main export that they have, semiconductors. And on semiconductor technology, if you're talking about integrated circuits, they consider mainly mainstream CMOS. If you're asking, sir, why not bipolar? Bipolar needs a lot of voltage. What about, sir, gallium arsenide? Gallium arsenide is expensive. What about, sir, silicon on insulator? Well, silicon on insulator is actually trying to answer the problem of CMOS. But then again, because you put an insulator on within the structure, it's gonna be more expensive. But there are pros and cons in this, which I will reveal later on. So we talk about CMOS. Okay, so what is CMOS? It stands for complementary metal oxide semiconductor. When you say complementary, there is an N MOSFET and a P MOSFET. And when you say N MOSFET, you actually are referring to the polarity of the channel. So when you say again NMOS for the students, you're actually referring to N channel MOSFET. Sir, if you're asking what is channel, well, it's just the bridge between 2 regions of your transistor. So if you talk about NMOS, you're referring to an N or negative polarity channel. And then when you talk about PMOS, you're referring to some positive polarity channel. Okay, so now if in your circuit you have NMOS and PMOS together, you call it a CMOS circuit. Now, the name itself is called field effect transistor, FET, because whenever you hear field effect, you are referring to something like voltage controlled. Because voltage actually relates to electric field. So what is electric field? If you try to remember what electric field is all about, well, electric field is actually voltage over distance. So anything that refers to something that has field effect on it, you're actually considering voltage controlled. That is why for the students, you will hear of a voltage control device, and that is referring to field effect transistors. So in this scheme, where does voltage controlling come in? And that is mainly to create the so-called channel. So when you say create, you refer to that as being to enhance the channel. Enhance refers to create, because notice, so here is a very nice picture, simplified picture of a cross section of a CMOS. It consists of NMOS, and PMOS. And notice that there are actually 4 terminals. And we know that you have your gate. That stands for the gate. You have your drain. You have your source. And the surrounding environment that we call bulk. You know, there is another word to refer to bulk. That is called body. And sometimes it is also referred as substrate. So yung bulk is telling you the surrounding environment ng transistor. Sometimes they will call it the substrate, or sometimes they will call it yung wafer. The wafer itself. Now, by inspection, notice that for the source, let's say that if you take a look at NMOS, for the source you have these elements dito are diffusions. They're called diffusions. They are called diffusions. And notice that between my source and my drain, there is no N plus diffusion. Now, I need to create something that will bridge between my source and drain, and that is what I call the channel. And if you're asking, sir, paano ko i-build yung channel? You use electric field or voltage. Ngayon, yung word na to build or create a channel, that is to say enhance. So, whereas kay PMOS, ganun din, I need to build the channel from source to drain in order for me na magkaroon ng current. Otherwise, you cannot have current flow. So, I need to add some voltage at the gate para mag-create ng channel, and that is via the electric field. And later on, I shall make a revelation on how to create the channel for PMOS and how to create a channel for NMOS. Okay, so that is CMOS. It consists again of 2 transistors, magkaibang polarity, isang N channel, isang P channel. And structure-wise, you will see the most fundamental to be looking like the circuit on your lower left. If you look at it on an electron microphotograph, it would appear like the following for more advanced processes. Okay. I want to mention, kung papansin niyo po dyan, I specifically placed a letter L. Yung letter L is actually referring to the channel length. So L is actually channel length. And you know po, itong channel length na ito is what they refer to as technology. Specifically, how the smallest channel length or the minimum channel length given for some processes in the semiconductor foundry is referred to as technology. Perhaps before, you're able to hear something like 45 nanometer technology or 0.35 micrometer technology, 90 nanometers, 22 nanometers, and so on and so forth. Yung mga yun refers to how far the smallest distance between my source and my drain for that specific process. And that is referred to as technology. And simply, ito yung distance between the source and drain or the minimum channel length. Sometimes they will also call it yung tinatawag nilang feature size. And you might ask, sir, what is the smallest that they can fabricate? That will be revealed in a short while. So I hope this is clear for everyone. And moving forward, so why should we bother try to make devices even smaller? You know, before, siguro mga 15 years ago, that was the time na lumabas yung flash drive. And before, we are already very proud to have 128 MB of flash memory. And now, there is such an explosion po ng memory. There is now around terabytes of memory capacity, the size of a USB flash disk. So it's like 3 to 6 orders of magnitude more dense. And why is it so? While you're trying to maintain the size ng USB, it's because the device itself tends to scale down. What I mean is, the smallest transistor na I can ever fabricate actually becomes smaller and smaller and smaller through the years. So 15 years in the making, the transistor size has shrunk very, very much. And because it is smaller now, I can put more of these transistors given the same area. And so what if I put more transistors? Well, I can even create, so you can see yung naka box na kulay green dyan, that is for your flash memory. So there are two variants. You have NAND flash, NOR flash, and ito mga to are all transistors. So the more transistors you have, the more each of these are bit elements. So those are bit elements. So the more transistors you have, the more bit elements you can ever propagate or fabricate. Therefore, the more memory you generate. That is for the flash memory. So sabihin, lumiliit yung size yung transistor, even if you try to maintain the area. And it makes sense na you can put more of these very small devices onto that particular area. And there is actually a nice comparison between the MOSFET and the bipolar junction transistor. If you try to look at the size of a MOSFET, it would appear like this crosshair. And if you look at the size of the bipolar junction transistor, this will be this big. And so if you talk about memory, I cannot build too much memory elements kapag si bipolar junction ang ginamit ko. Kasi, technically speaking, they're big. Si MOSFET is very small, and they continue to scale down. They become smaller and smaller through the years. And so, because they are getting smaller, you are able to realize denser memory elements. And then, parang ganito, if you have on a certain work area, tapos marami kang workers in that area, then you tend to have more outputs. That is why you have more computing power, ergo you have smarter processors. So you have more memory elements, and you have smarter processors that can do floating point computation. The metric now is using flops. Sometimes teraflops times 10 to the 12. Flops would mean floating point operations per second. So that is floating point operation per second. So some are actually doing teraflops already. That's very fast, especially when they're operating using floating points. That means high accuracy. Okay, so this is floating point operations per second. Ops per second. Okay, so with all of this, so you might be thinking, gawin natin, make them just smaller and smaller. So if you try to make them smaller and smaller, well, you have yung smaller, more memory elements, mas dense, and even smarter processors. Pero ano magiging problem? You cannot just control them. It's gonna be very difficult to control them. Okay, so yung paradigm ng pagliit ng transistor, yung MOSFET becomes smaller and smaller, is actually observed. It was observed before by one of the founders ni Intel, and that was observed by Gordon Moore. Kaya you will hear of Moore's law. So Gordon Moore po is one of the founders of Intel, and he observed na if you try to reduce the size of the transistor, definitely there's gonna be double yung amount of nito mga transistors. And he looked at the timeline, and approximately, sabi niya, ito yung famous Moore's law. Moore's law would say that the number of transistors on a chip multiplies by a factor of 2 per 18 months. Pero you know po, that was before. So you might be wondering, sir, what do you mean that was before? Yung pag-scale down or pag-shrink ng transistor size was all that good before, but now they cannot anymore. Okay, so I'll tell you that in a short while. The main reason for that is, if you try to fabricate even very, very small devices, it's gonna be very hard to fabricate. So on the level of complexity, it's gonna be very difficult. And so to address yung difficulty na yan, you need more capacity. And if you need more capacity, that tends to be more expensive. And worse, since yung pag-fabricate ng mga ito is very difficult already, and the device itself is very hard to control kasi napakaliit niya. Okay, so I will lay down the cards later on what I mean about them being unable to be controlled. But for now, we can look at the trend of scaling to be something like this. So if you try to plot year, this is year, and then this is the number of transistors. You will notice that it has the following trend, but it plateaued. So ibig sabihin, you cannot anymore try to increase the number of transistors through the years. So you can say na before it was Moore's law, the Moore's law era, which is etong period na ito, Moore's law era. But then again, you cannot do that anymore. You cannot just make the transistor smaller. Number one, complexity. Number two, very difficult to control. So, ano yung transistor that they were able to fabricate, which is the smallest as we speak? Okay, so memory density evolution. So notice that there is such increase in terabytes per square inch through the years, and that is driven by Moore's law. Pero there's something actually able to challenge yung semiconductor memory, and that is using magnetic head. Okay, I mentioned later on, you will notice na the next memory cell it's like going back to the era of the cassette tape. Kasi in the future memory element is gonna be magnetic. And there are several reasons for that. Because yung mga USB, yeah, you can store some memory there, pero after several years, yung data stored there will not be there anymore. Kasi all of those, especially if they're too small, they tend to leak out. So nawawala yung stored memory doon. Whereas for magnetic memory, nandun pa rin yun. Kaya they want to somewhat go back to the magnetic type of memory. Okay, so so this is how a MOSFET would look like, cross-section. And then this is how it would look like if you look at it in a microphotograph. So there are actually several layers. And some of those, again, they refer to it as technology. And if you remember, technology, again, refers to the minimum channel length that you can ever fabricate. So there are actually several of them. You have 0.5 micrometer, which is very, very old. And then you have 0.35 micrometer, then 0.18 micrometer. And it can even go forward with 90 nanometer, 65 nanometer, 45 nanometer, 22 nanometer, 10 nanometer, and so on and so forth. So again, ito yung distance between, itong technology na yan is the distance between the source and the drain. The smallest. And if you look at it dito, yung transistor is actually ito. So where's your channel? So this is your source or drain. And then ito yung aking gate. And ito yung aking lumalabas na channel with a channel length of L. And ano naman to? You know, if you try to make the transistor smaller, there's something that you cannot just scale down. Guess what? Itong problematic region na ito, they are just your contacts. So, what? Kung if may contacts na ganito? You see, yung contacts themselves are big. Kaya, they are actually limiting factors whenever you want to create very high dense memory elements. Lalo na kung halimbawa, think about implementing a NOR. Pansin nyo, lahat netong mga transistor neto, marami silang contacts, right? What do I mean? Yung contacts na yan, pwede mo tignan as nodes. So ito ay node, 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 etc. And imagine itong mga node na yan, ito yun, itong contacts. And that consumes quite a lot of area. So what happens to your design? Of course, you need some contacts. Well, you cannot have a high density NOR kasi it needs a lot of contacts. Right? But you can have a high density NAND. Pero what would be the problem? The problem is, see, iisa lang ang bit line dyan. So I need to, for example, nandito yung aking data, let's say 0. Kailangan niyang dumaan papunta dito until it reaches the output. So lalabas si NAND mabagal. Si NOR mabilis kasi yung output ni NOR dito agad. So accessible agad yung output. Pero si NAND hindi. Pero si NOR, marami siyang contacts. So lalabas, mas low memory si NOR. Si NAND, lesser contacts, therefore, higher density. So see, just looking at the topology ng circuit gives you an insight on gaano karaming transistor ang pwede ko ilagay and sino mabilis. Si NOR po ay mabilis na flash. Si NAND yung high density. So you cannot really have yung best of both worlds. Like, mabilis and at the same time high density. And you know what? Sa flash memory, ang problema talaga ay ito, yung contacts. Because they are too big. They consume a lot of area. So ito yung cross-section ng transistor. Just to note pala, no, whenever sa semiconductor, they call it semiconductor foundry, semicon foundry. Sila yung mga gumagawa ng transistor. Foundry. Okay, so they add some labels like, so for example, yung ginawa ng UMC, 0.5 micrometer technology, that means, ito again, yung pinakamaliit na size, L minimum. Ano ibig sabihin nito? Ito mga to refers to double poly and then double metal. So, ngayon, pansinin nyo, bakit ko kailangan ng metals? Para saan ang polysilicon? So, ngayon, kung titignan nyo yung, okay, perhaps meron pang mas magandang picture dyan, ano? Okay, this is to show yung MOSFET. How to build the MOSFET. Bottom up. So, yung substrate, it is actually P-type. And ano po yung isa pang pangalan ng substrate? Ito po yung wafer. Bakit po siya P-type? Quite a long story, pero ganito kasi yan. Before, gusto nila, syempre, dapat mabilis yung transistor. Mabilis siya mag-switch. Yung P-type kasi, mabagal siya. Pero, kung gagawin ko lang siya na parang pedestal, where I'm gonna build mga NMOS transistor ko, well, that reduces yung fabrication complexity. Kasi, I can readily put yung NMOS transistor ko on top of P-type. No other complexity needed. Kaya, before po kasi, they want all NMOS. Kasi ang NMOS, mas mabilis kaysa kay PMOS. And kung P-type yung wafer, specifically, if they try to put dito boron, remember yung trivalent material? Tatlo yung valence. So, boron yung ginagamit because itong boron has very good solubility, is very, very soluble kay silicon. Solubility. Very soluble or can be dissolved kay silicon. Okay, so they dope itong aking wafer by boron atoms to some concentration to make it P-type. Again, boron is trivalent. Then after that, I can just put my NMOS. So, let's follow the steps muna, no? So, yung ilalim is actually, may legend yan. This is telling you the different layers to create your transistor. Okay, so, now, moving forward, sorry. The next phase is create your N-well. So, paano nila kine-create ng N-well? Maglalagay sila ng pentavalent material. High doping of pentavalent. And amongst the 3 pentavalent materials, ano kaya yung ginagamit nila? So, madalas silang ginagamit ay phosphorus. Phosphorus. Bakit ganun? Kasi they're assessing yung solubility ng phosphorus kay silicon. Sabihin, pwede siya ma-dissolve. it can readily mix well over some temperature. And in terms of cost, well, if you compare it to arsenic and antimony, it is way cheaper. Kasi if you have your materials na expensive agad, wow, if bibili ka ng IC, it's gonna be very expensive kasi yung raw materials to build them are already very expensive. So for them to create yung well, they put a lot of doping ng phosphorus atoms to make yung aking substrate achieve an N-type region or the N-well. Okay. We can learn something from this kasi sometimes, there's something na oversimplification. What I mean is, di ba pag diode, ang alam natin, diode is ganito. Tapos we label this as the P and then the N. Pero technically po, this is not the structure of the diode. This is just a simplification. So again, yung P-type, that is yung pag denote mo siya with trivalent atoms, specifically boron, and N-type, kapag denote mo yung silicon ng phosphorus or pentavalent, this is just a very simple representation ng diode. You know what a diode looks like? Is actually on the right side. The diode would start with a P-type material. You can say this is the substrate. And then, anong gagawin nila? They will try to put a lot of doping sa substrate. So they'll put a lot of doping to create N+. And then, sa aking substrate, of course, gusto nila magkaroon ng contact dyan, maglalagay sila ng high doping na substrate, P+. And then you create your diode. So, hindi siya literally ganito yung structure. Meron kang P-type, meron kang N-type, then fusion. Actually, mag-start yan sa P substrate, and then maglalagay siya ng high doping na N+ doon, and then maglalagay lang siya ng P+ dyan to just have a good contact. So, for contact lang siya. And that is your diode. The real diode. In actual scenario po, ano yung pinaka-important parameter sa isang diode? Actually, yung pinaka-important dyan would have to be yung depletion region. Kasi, ito yung technically speaking, mahirap makita yung PN junction. And in industry, how will they try to find it? They try to find it by profiling yung electric field. So for example, ito yung aking a simple representation of the diode. Then, ang ginagawa dyan, let's say meron akong electric field dito. This is electric field. Tapos, let's say, di ba meron po na-form na depletion region sa pagitan nito? So you have a depletion region, tapos, ano yung meron sa depletion region? Those are ions. Ion filled region. Kasi, bakit sir ion yan? Kasi, nagtatagpo yung mga holes sa P-type at electrons ng N-type sa junction. Kaya, nagkakaroon ka ng, so nakikita yung dalawang types of charges for the P-type, yung mga holes, and then yung sa N-type, yung mga electrons, nakikita sila sa junction, therefore, na-ionize yung N-type na atoms and P-type na atoms. Kaya, nawawalan o nagmamigrate yung electrons from one side to the other. Okay? So, na-ionize sila. Now, pag tinignan mo yung Gauss law, the Gauss law is telling us that the divergence of D, katakot to, no? Divergence of D is equal to Q enclosed. So, and so what? Cut the long story short, forget about this. Talk about what does it mean. So, ganito yan. If you try to profile an electric field, dito ka lang makakakita ng electric field. Dito sa depletion region. So, if I try to draw it here, zero sa electric field, then suddenly, rise yan, then down, then like this. And yung kailan non-zero electric field, that only happens kapag nasa depletion region ka. Okay, so, and they try to profile electric field, and when meron ka nakitang peak, eto, Emax, or maximum electric field, that is where the junction is. Okay, so very important to find the electric field across to find the junction. That's how they try to find it. Okay, so this is all about the diodes. I was just referring to kanina how to build yung diode. So again, we start with the P-type substrate, and then naglalagay ka ng N diffusion or heavy doping of N-type to create your PN junction. And then how do they find the actual location of the junction? They profile it by electric field. Bakit, sir, electric field ang ginawang basihan? Kasi if you follow Gauss' law, there will only be an electric field kapag may charge enclosed. And anong charges yung enclosed dyan? Remember, that is ion field. So maraming ions dito sa depletion region. So charge enclosed yan. Therefore, yung divergence ng electric field or ng flux density is not gonna be equal to zero. Therefore, may electric field ka dyan. Yun. So, that is how they try to find the junction. Then, if you're asking, bakit meron pang N-well? Well, that is gonna be yung surrounding environment ng PMOS. So this guy will be the surrounding region, surrounding environment for the PMOS. Or if you say surrounding environment, this actually refers to the body. Okay. So notice that the next phase would be yung shallow trench isolation. Sometimes they say this is STI. Well, this is to isolate between devices. Mahirap kasi kapag wala kang harang. Pwede mag-short yan, or specifically, meron kang pwede ma-activate dito, guys. You will be able to activate yung parasitic na BJT. Okay, so to avoid that, to make the long story short, let's add some isolation. Now, after that, naglalagay sila ng threshold implant. Para saan kaya itong threshold implant? Well, that is for to prevent leakage. You will learn about leakage in a short while. So they add additional implant. Then after that, may na-form na ganitong region. So, ano itong red na to? Ito yung polysilicon. Pag sinabing poly, it seems to have some crystalline structure. Pero hindi siya purely crystalline. But anyway, and then itong sa baba, this is your, sometimes you refer to that your tin oxide. Okay? Or you call it your gate oxide. Now, there's a keyword called gate. So, yung gate is formed by a polysilicon, which is actually an insulator. And then, merong insulating property yan. And then you have the oxide. Then what is the next step? So, kung itong kulay pula na yan forms my gate, the next step should be, so you need some sidewall spacing. That is mainly to create some barrier then for leakage. And then, next step would be, so meron kang ilalagay na P plus around N well and N plus around P well. Para saan itong P plus na ito at N plus for around my P well, they now form this could be source or drain. This could be your source or drain. Likewise, source or drain and source or drain. So now you have a transistor on the left that is inside an N well, and notice na P plus yung kanyang source or drain. And therefore, kung P plus yan, I need to create a channel here, and yung polarity ng channel I going to be P type. So it's going to be a P channel. And therefore, sabi ko kanina, yung polarity ng channel defines a kind of MOSFET. So therefore, this is a PMOS. And on the other side, notice na N plus or negative polarity yung source and drain. So kaya dapat magkakaroon ako ng negative kind of channel. Kaya meron ka ritong N channel. So kaya yung nasa right side mo ay NMOS, yung nasa left side ay PMOS. Sir, para saan itong mga N plus na to na naka-connect kay N well? Or itong P plus na ito na naka-connect kay P well? Yan po ay contact. Gusto mo kasi, you can readily access itong N well or yung P well. So you need to have high doping para bumaba yung contact resistance. So ngayon, kung yan yung contact dyan, anong layer ito? Anong electrode yan? This is now going to be your bulk or the body. So now you have your gate, yung kulay red, source or drain, then bulk. Now, you might be asking, sir, how do I connect each one of them together? Simple lang. I need, kung itong transistors na ito ay nasa first floor, kailangan kong umakyat ng second floor. And how do I do that? Kailangan ko ng stairs. And kung kailangan ko ng stairs, meron tawag doon. But first, kailangan yung stairs na gagamitin ko to go to second floor, hindi dapat masyadong mataas yung pitch or kailangan ko napaka taas na hakbang to go there kasi mahirap umakyat. Kaya naglalagay po sila ng tinatawag nilang polycide, hindi po to variant ng insecticide. Polycide, salicide, they're actually called silicide process. And para saan po yan? Kung imagine niyo po na kailangan ko ng hagdanan to go to second floor, itong mga silicide process na ito, na ina-add, ensures na yung pitch o yung hakbang between hakbang dun sa ladder natin o sa stairs ay hindi masyadong matarik. So mas madaling umakyat. So dito ngayon, sa perspective na ito, itong silicide process, they reduce yung contact resistance para mas madaling umakyat yung charges. Contact resistance. Otherwise kasi, kapag may contact resistance dyan, well, mahirapan umakyat yung charges, so therefore, hihina yung current. Now, after that, so naglagay sila ng silicide blocks such as polyside and salicide. After that, they can now, okay, you have your insulation. Insulated yan. Sometimes, ang ginagamit na insulation is oxide. Fox, sabi nila, that stands for field oxide. Sometimes, they just use glass. Okay, on top of that. So, I'm now ready to go to second floor. So, ngayon, I need itong mga tungsten plugs to go to second floor. And itong tungsten plugs, may tawag dyan, they are called contacts. So whenever you try to go from the first floor where your transistor is, you need the stairs to go to second floor in the form of contacts. Ngayon, ano itong mga black na to? Those are metals. Ito mga to. Okay? Then, ngayon kasi, we talk about the billions, millions to billions of transistors. It's gonna be very hard for you to really connect them together using just the second floor. Parang ganito rin. It's very hard to develop a PCB design sa isang integrated circuit na napakaraming components. So what you do is, you add stacks. So mag-stack ka. So stack up para walang mag-short sa iyong PCB. Or you can say magja-jumper wire ka. Ngayon, kailangan kong umakyat sa third floor, if ever I need to connect to more transistors. Kaya, I need more stairs, I need more plugs to go to the third floor. And ano yung mga compartments na meron sa second floor, third floor, fourth floor, fifth floor, etc. They are all metals. So ito you can say this is metal 1, metal layer number 1. And then, may stairs ka na naman. I just want to mention po, no? Kapag aakyat ka to another metal layer, let's say metal 2, and then later on, I'm not sure kung meron pang susunod dyan. Ano? Oops, meron pa nga. Meron ding metal 3, for example. Meron kang inaakyat ang stairs between second floor or metal 1 until the topmost floor. Ang tawag dito ay vias. Metal vias. So, it is quite different from the contacts. Kasi ang contacts po, yan ay between metal 1 and everything below it. Ano tong anything below it? Ito pwedeng diffusion to create your source or drain. Pwede yung gates, yung polysilicon, pwede yung bulk, and so on and so forth. Tawag doon, all of these are called contacts. And then, all interconnects between metal layers is called vias. Based on experience po, when I tried to design integrated circuits, usually yung area ng via is bigger than contacts. Okay. So sometimes they could have the same material like tungsten or even copper or aluminum. Depends on the process. So this is the cross-section of the transistor. Well, let me check kung meron pang susunod na layer. Wala na. Okay, so you see, kung masyadong dense ang iyong circuit, even metal 3 layer is not enough. let's say, talk about millions and billions of these transistors na kailangan ko i-connect together. Let's say, gagawa ko ng napaka-high density na NAND flash or processor. I cannot just connect all of these transistors in 3 metal layers. So I need to go higher. So kaya, for older processes, they only have around, let's say, kanina you might have noticed meron akong sinulat na 2P2M. Yung M is metal layers. So ibig sabihin hanggang metal 2 siya. And then nagiging ano yan? 2 polysilicon and then 4 metal layers. Then guess what? Meron yan magiging 1 polysilicon and then 6 metal layers. And then 1 polysilicon and then 9 metal layers. Pansin nyo, you would notice na ano yung tumataas? Tumataas po yung count ng metal layers. 2 metal, 4 metal, 6 metal, 9 metal. Tanong, bakit kailangan tumaas yung bilang ng metal layers? Kailangan mo kasing i-connect itong very high dense na chip na ito. And bakit kaya metal? Kasi ang metal, mababa ang kanyang resistance. So ngayon, why would it be important to have low resistance? Kasi if you have high resistance, for example, may i-connect akong dalawang transistor na ganito. So I have this transistor. And then I want to connect it to the other side, for example. So I have transistor 1 and transistor 2. I'll label this as M1 and M2. And then, pinaraan ko siya sa napakaraming via. Lalabas na, magkakaroon ako dito ng resistance. And you can say that that is RC. Contact resistance. So let's say this is gate of the first transistor, then I have gate of the second transistor, and vice versa. So, ang current po kasi, pupunta yan pag ganito. Yung kulay blue na yung trace is current. Pag meron siya nakitang resistor, ano po ang nangyayari? Papasok si Ohm's law. Kapag merong resistor at may current, merong lalabas na voltage drop. So magkakaroon ka ng voltage drop across this. And kung magkakaroon ka ng voltage drop, that is considered loss. Okay, so pag meron kang parasitic na resistance, something that you really don't like, tapos may dumaan na current doon, at magkakaroon siya ng voltage, you have losses. So itong voltage developed across here, you have loss. So that's why you want to have the least value of parasitic resistance. And you can achieve that by having more metal layers. Yung polysilicon kasi, that is actually a resistor. Okay? So, if you're asking, you might be asking then, so bakit before you have 2 polysilicon? By the way, yung polysilicon again is used to create capacitors. So yung P dito is capacitors. Polysilicon, yung letter P dyan, pag double poly yan, that is used for capacitors. And that is very important po kapag analog design. Pag digital, you hate capacitors. So whenever you see a poly dito na dalawa, that is used to create a capacitor called PIP. Sabihin, poly insulator poly. This is a capacitor. You will see its structure later on. So yun. So now you see, as time goes by, dumadami metal layers para walang masyadong losses or walang masyadong contact resistance or parasitic resistance. Kasi for each parasitic resistance, you actually create losses. And that is gonna be detrimental po kapag digital. Okay, so this is the structure of a MOSFET. Hope that this is fairly clear enough. If you have questions po later on, I would be glad to answer. And moving forward po, how do they build the transistor? It's actually more of a lithographic process, photolithography. It's almost similar doon sa how you build the PCB. So first, they start with growing the field oxide. So you have the kulay gray area, and then they implement yung first mask, which they call the N-well mask, para ma-define yung regions ng N-well. Kaya na-form nila yung N-well. So they use here N-well mask, and then matatanggal yung portion of the oxide, then magdi-diffuse ng N-well, high doping. Then after that, i-define naman niya yung susunod na region. For what purpose? Well, this is for you to place your NMOS. And dito naman sa N-well, you create your PMOS. So on this end, so next phase is you grow the gate oxide. Gate oxide, again, is called tin oxide. Tin oxide. So you use the tin oxide mask for this. And then maglalagay ka ng polysilicon. Para saan? That is for creating your gate. And so you have this gate. And then what you do is remove portions of the polysilicon. You now incorporate yung poly mask. This is now polysilicon mask to create the gate. Kaya after yung mga masks na ito, you can now have regions for your gate elements as shown here. And then next, you define ano yung N plus to create your N-channel MOS. And then you create your P-channel MOS on the other side. So this time you create your N, either N or the P diffusion masks. So you use your masks here. And then after that, you now define where is your N plus or your P plus. And what would be next would be provide the insulation or the nitride. So sometimes you can say this is your insulation alongside yung field oxide, insulation. And then what's the next thing to do? Create the contacts. So it's gonna be the next series of steps will involve contact mask, and then metal 1 mask, and so on and so forth. So ito po yung steps. Yung, let's say magpapa-fabricate ka sa isang semiconductor foundry, ang ginagawa doon ay bibigyan ka ng isang technology. So for example, yung isa sa mga prominent, though very mature technology, but fairly very old, is yung 0.35 micrometer technology. So the 0.35 micrometer technology, for example, of a company called TSMC, which is one of the premier companies that fabricate transistors, it has 2 polysilicon and 4 metal layers. So, papafabricate ka sa isang semiconductor foundry, so they will be giving you their technology, 0.35 micrometer technology, that has double poly and 4 metal implementations. So, magsasubmit ka sa kanila ng design, and yung design will consist of designs for the masks. So eto sa step 5 pala, I missed to mention, is a thin ox mask. So you have N-well mask, thin oxide mask, poly mask for your gate, N+ diffusion masks, and for your contacts, for metal 1, and so on and so forth. So ang binibili mo actually sa kanila ay yung mga mask patterns that they will customize for your design, but you need to pay that. So the more complex the design, the more masks you will need, which makes it more expensive. Okay, so ito yung ibig ko sabihin ng mask. So una, whenever you want to fabricate a chip, you have itong photo mask. Ito yung pattern na you are actually laying out to fabricate the transistor. So ginagawa dyan, meron ka UV light sa taas, meron kang lens para mapaliit yung 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 pattern, tapos ito yung wafer. So meron siyang photoresist. If you ever tried developing your PCB, so gumagamit din niya na ilaw, UV, para mas malinis or mas fine yung kanyang pag-burn o pag-develop. So meron kang photomask, pattern could be the N-well, could be yung tin oxide, could be yung polysilicon mask, N or P+ diffusion mask, and so on and so forth. And then tatamaan yung photoresist doon sa wafer, and after that, may iwang patterns. And yung mga patterns na yon, either parang sa PCB, na etch away or nare-retain, depende sa klase ng photoresist, and then you can etch them, sometimes you call it developing, and then you put diffusion. So ganun yung steps for the development of your circuit. Now, as a designer, you are the ones who provide the patterns for the masks. And those are in the realm of layout. So pag nag-apply ka sa isang work, and then you are a layout engineer, you're actually developing the layout to create the masks for the different layers on your transistor or on your circuit. Now, in real scenario po, hindi perfect ang alignment ng photomask, ng lens, at pati noong wafer. Kaya nagkakaroon po ng skewing as a result of this misalignment. So, moving forward, I can skip this. Some of the aspects on the fabrication end, kasi you need to anneal it. When you say anneal, you try to use heat para mag-uniform yung distribution ng mga atoms after you dope it. So thermal annealing allows you to have a more uniform distribution of the atoms. For example, meron kang P substrate dito, tapos ginamit mo ng thermal annealing. So una, nag-diffuse ka dyan. Okay, so nag-implant ka dito, tapos naging ganito siya. Definitely, you cannot control ano yung mafo-form na region. So, naging N+ ito. Pero, bakit siya? So, gagawin mo dyan, tataas mo yung temperature. So, you can increase the temperature. What happens? Yung temperature kasi adds. Actually, that is a form of energy, no? Thermal energy. So, what happens dito ay Itong mga charges natin, try to wander around to create a more uniform surface. So that is called thermal annealing. Now, here's the thing. Kapag ininit natin yan, hindi lang naman ito mga N plus regions na ito yung gagalaw. Kaya later on, pati yung oxide, yung nakapaligid ng oxide sa aking transistor, mag-extend din to create yung aking bird's beak. And because of that, parang mag-i-invade siya ng territory. Sabihin, liliit yung effective size ng transistor. So these things should be accounted for when you're trying to do design. So moving forward, because you have these issues like after annealing, so some of the materials tend to extend or expand, so trying to occupy some other areas, especially nung transistor, nagkakaroon ka ng so-called skewing parameters. And these are dependent on yung how good is the fabrication. So ngayon, meron ka ng XL, meron kang XWN and the XWP. Ito yung XL is the difference between the drawn and actual size of the length. And then oxide thickness. And then you have your resistivity ng active layers and how much change in VTH happens. So what does it mean na lang to say skewed? Assuming, for example, meron kang wafer dito. Okay, so may wafer yan. May cut dito yan, ano? Para to serve as alignment. So yung wafer na yan, kasi meron yan division na ganito. Okay, so meron siyang divisions na ganyan. And each of those elements is called a die. Ito yung chip itself. So ngayon, let's try to look at yung oxide thickness profile nito. Let's try to plot it from, let's say from here to there, across the width or the diameter of this wafer. I'm actually plotting po yung kanyang oxide thickness. So what oxide thickness are we referring to? Ito po yun. So, di ba when I try to build yung transistor, ito siya eh. So meron ka ritong this is your polysilicon, right? So this is your polysilicon, and this is your tin oxide. Okay, and then your surrounding environment, for example, that's P substrate, you can say this is a semiconductor. Semicon. So ngayon, yung thickness ng oxide is this. TOX. They want to make it very thin, but they cannot make it very, very thin. Too much. Okay. So, oxide, ano yung before ang ginagamit nila, which is fairly more abundant, is yung silicon dioxide. Okay. So, kung titigyan nyo, no? Bakit nga pala siya tinawag ni MOS? Kasi before, yung poly is actually metal. Metal yan. So, okay. So, let me try to quickly draw it So this is metal, tapos meron kang oxide. So parang may M ka rito. May oxide ka dyan, then semicon sa baba. Kaya MOS. Ganun po yun. Kaya MOSFET yan. Kaya lang, due to some limitations by using metal, they changed it to polysilicon to make it more reliable. Okay, so what I'm trying to say dito sa aking graph, going back, is ang oxide thickness is not uniform. So for example, meron akong transistor na nandito. Yung oxide thickness niya is very small. Tapos meron akong transistor sa kabila. Ito yung kanyang oxide thickness. So ngayon, for the same batch of wafer, I will have two-dimensional variations maski sa oxide thickness. And you know po, itong oxide thickness affects one very important parameter, which is yung threshold voltage. So therefore, kung mas makapal yung oxide thickness towards the left of the wafer, that is equivalent to saying yung transistors na mafo-form ko to the left of the wafer tends to have higher VTH than those towards the right. And VTH is the amount of voltage that you need to add to the gate to create the channel. Less than that, you don't have a viable channel. So what this is telling us is, itong slide, across my wafer, hindi pare-pareho yung nagiging result. Sometimes, it's easy to say, oh, we can actually make it simpler this way. Pag let's say dun sa typical lab, sa electronics, so meron kayong famous transistor na 2N22222. I forgot how many 2 yan. Magkakaiba yung kanyang beta whenever you, for example, meron kang multimeter, tapos kumuha ka ng isang transistor na 2N222, tapos sinalpak ko siya doon sa meter, sinukat ko yung beta, kinuha ko yung HFE niyan, or yung beta factor, tapos kumuha ko ng isa pa ulit, iba yung lumalabas na value. You call it batch spreading. Ganito rin yun. So ngayon, magkakaiba yung lumalabas na electrical properties ng transistors even across left and right of the die or top and bottom. So, isang proseso yan, pero dahil sa position nila, naapektuhan yung electrical characteristic. You can call that batch spreading, or you can say that they have skewed parameters. If you're asking, sir, how do we try to make it at best effort, similar? Depende na po yan sa layout engineer. Ginagamitan nila techniques like common centroid layout. Meron silang techniques to try to solve this issue. One is common centroid, which is yung pinaka-famous. Or they do a lot of averaging using something called interdigitation patterns. Digitation patterns. Okay. To try to address issues of variation or skewing of the parameters due to process-related variations. Okay. So, some takeaways of this slide, bakit siya tinawag na MOS? Number one, originally, yung top layer above the oxide is metal. So, meron kang MOS. Yung O is for oxide. There's actually another name for MOS transistor for the students. So, you have MOSFET. This is also called, if you look at the books, this is called IGFET. And why is it called IGFET? Yung IG stands for insulated gate. Insulated gate, and ano yung insulation yan? Etong oxide. So this is your insulator. So dapat gumamit ng oxide to create your MOS. And MOS, FET, is also called insulated gate. Okay, so, but then again, you need some techniques to address issues on variations across the same wafer, even if they are of the same circuit topology. And that can be done mainly by layout. And they do common centroid, or they try to pattern it in a way na interdigitated para lalabas sa average yung parameters. Okay. So, now moving forward, ito po pala yung tsura ng symbols ng transistor, which is normally used. Ito yung layout na itsura. Sorry, this is the layout. And these are your symbols. So then again, please do remember na yung distance between the source and the drain is L. And the smallest L that I can ever create is called technology. Okay? So, I want to mention now, whenever you try to design a transistor using the MOSFET specifically, you're actually trying to define how much length, and then two-dimension kasi yan, how much width. So you have the width, and then you have the length. And that is one design parameter. Normally kasi po, you need to define what is the width and what is the length of the transistor. Now, if you look at it in the layout view on the lower left, you're gonna have, this is going to be your length. And yung two sides na yan, this could be the source or the drain, or this could be the source or the drain. And where's the width? Ito yun. Ito yung width na lumalabas. So ngayon, sa layout, you try to define how much length and how much width. And even on design, you need to define how much width and how much length. You will appreciate that more kapag nakita niyo yung equations ng MOSFET. So these are the symbols. Just want to note po, no? On the aspect of analog design, let's try to put two worlds together. Okay, so you have analog design. Magkaiba po kasi yan. And then on the left corner, you have digital design. Okay. And ano ngayon, sir? I mean, why do we have two worlds? Ganito kasi yan. Okay. Wait, change color lang ng pen. Palit. Yan. Sa digital po kasi, ang symbol ng transistor is just like this. Kung NMOS yan, ganito. And kung PMOS yan, ganito siya. May bilog. Kay analog naman, on the other end, ito yung symbol niya for NMOS. This is your NMOS. And then, the other end naman, your PMOS. Now, if you try to do a head count, ilang electrodes yung accessible sa analog and digital? Of course, ito yung gate. Kasi itong region na ito yung oxide. Oxide yan. Ano itong terminal na ito? This could either be source or drain. Kasi, technically, they are really interchangeable. Especially, for example, if you do an experiment, bumili ka ng kahit JFET lang, yung dalawang terminals na ay interchangeable. Likewise, sa other side, ito yung gate. Ito yung gate. And then this could be the source or the drain. This could be the source or the drain. Source or drain. Source or drain. But notice na meron pa yung may arrow. Dito, ito yung bulk. Ito yung bulk. For digital design, wala nang implied na po yung bulk. What does it mean? So for digital, I can note here, for digital design, well, the bulk for NMOS, let's say if I draw yung NMOS dito, the symbol na ganyan for NMOS is equivalent to yung analog component na ganito, pero yung kanyang bulk ay grounded na. Whereas for PMOS naman, I can put on the other end. So kung PMOS naman, yung may bubble, may bilog, yung kanyang symbol ay yung PMOS symbol na may arrow, pero itong arrow na ito ay connected kay VDD. Ang VDD po ay positive supply by default. So yung NMOS, yung kanyang bulk is connected directly to ground, whereas for PMOS, yung kanyang bulk ay directly connected to positive supply or the most positive supply you have or VDD. Yun ang difference. Kasi po sa analog design, yung bulk potential na to or body potential, yung voltage na ilalagay mo dyan is also one important aspect of the design. For example, gusto ko naka-reverse bias itong bulk and my source. So lalabas, tataas yung threshold voltage ng NMOS. Sabihin, mas maraming voltage yung kailangan to create the channel. So lumalabas high VT process, high VTH process. O isa naman kapag binabaan ko yung potential across bulk and source, lalabas na pinapababa ko yung threshold voltage niya. So lalabas low VTH na scenario. And those are very important sa analog design. Kasi meron po kasing tinatawag na bulk effect. Sa digital, wala pong ganito. Okay, so this will be revealed later on. So, takeaways po from this slide. Yung MOSFET po, you actually define yung kanyang length and probably later on, you will call the aspect ratio. Parang po sa mga television, 16:9. So sa MOSFET din po, you call it aspect ratio. This time width and length. What else? So for digital design, yung bulk ng NMOS is by default automatically connected kay ground. Yung bulk naman ng PMOS ay automatically connected to the highest potential or the supply voltage, VDD. Okay, so moving forward po, this is how very basically, okay, so I'll answer some questions later on po. So stay tuned. So how does the MOSFET work? So the MOSFET works by applying the gate voltage. We have here 4 stages of how the MOSFET create the channel. So initially, we apply a VDS. So we are at stage A. So notice that yung kulay pink po na yan, that is for your depletion region. So ito ay depletion region. Why is it po na may depletion region agad? Remember, kapag may na-form po na PN junction, automatically, nagkakaroon ng depletion region. Kasi yung majority carriers between both sides, yung positive and N or the negative, magmamigrate sila to the other side. Pag nag-migrate sila, parang yung electron from the N-type, tatalon siya papunta sa P-type region, makakakita ng hole, ma-attract siya doon, therefore yung N-type nabawasan ng electron, whereas yung P-type naman, na may mga holes sa structure niya, which creates the net positive charge, mapupuntahan ng electron. So nagkakaroon si P-type ng extra electron. And because of that, yung P-type sa region ng junction, nagkakaroon siya ng negative ions kasi nagre-receive siya ng electron, whereas si N-type nagiging positive ions kasi nababawasan ng electron. So yung junction na yan, yung mga ions dyan, wala nang charge carriers doon. Charge carriers na pwedeng gumalaw. Kasi, for example, meron kang PN dito. So, for example, this is P and this is N. So, ngayon, puro mga holes yan, mga positive yan. And then, makikita ito, pag na-form yung junction, so may mga negative ka dito sa kabilang side kay N-type. Mga charge carriers po yan. For N-type, those are electrons. For P-type, those are holes. Makikita ni electron yung aking holes on the other side. So lilipat siya doon. Si N-type nababawasan ng electron. So nagiging positive yung ions dito. Positive ions yan. Tapos pumapasok sa kabilang side, nalalagdagan ng electron yung P-type, nagiging negative. So kaya nagiging ion region yan. Ngayon, nag-migrate po yung charges. So ngayon, nawala yung free carriers. Yung free electrons sa N-type, pumunta doon sa free hole sa P-type. Tawag doon, charge recombination. So nawawala na yung charge. As a result nun, nagkakaroon ka ng depletion region. Dinideplete mo yung region. So that region is depleted of free charge carriers. So every time na nagkakaroon ng PN junction, nagkakaroon ka directly ng depletion region. Why is it po na mas makapal yung depletion region kay drain side kaysa dun sa source side? It's because of VDS. Kasi kung titigan mong mabuti, yung drain side, we're looking at an N-channel FET. Parang, if I look at yung sa drain side, so here, yung drain side is actually N+. Yung sa bulk is actually a P substrate. So ngayon, naka-positive yung aking N+, positive siya, and then ito naka-ground. So di po ba na ang lalabas na polarity ng aking drain, so this is my drain, and this is the bulk, is reverse bias. Ibig sabihin, yung N side is more positive than the P side. So kaya, naka-reverse bias yan. Di po ba pag naka-reverse bias ang isang diode, ang nangyayari ay nagwa-widen po yung depletion region. So nagwa-widen po ito. So pag nagwa-widen yan, well, there's actually a bad effect of this widening. But for now, let's accept that. So what happens? So ngayon po, wala ka pang ina-apply na voltage across my transistor. And this time around, I applied a VGS. So nag-apply akong VGS. What is the first thing that will ever happen? Kasi since positive po yung nasa gate, and this thing over here is an oxide, which is an insulator. So yung mga charges na ng P substrate na puro positive, may positive doon sa gate, may mga holes sa ilalim nito. Notice these holes. Ang mangyari po ay i-vacate ng holes yung region na yan kasi nare-repel siya ng positive. So ano po nangyari doon? Nagkakaroon ka ng depletion region sa ilalim ng gate. Kasi yung mga holes ng P substrate sa ilalim ng gate are actually pushed away by this potential, the positive potential across the gate. So ngayon, nagkakaroon ka ng depletion region. But wait, ano po ang nangyayari? So nade-deplete yan initially. So this is actually, B is more, you can say that is depletion phase. Depletion phase. Ibig sabihin yung aking, nasa ilalim ng aking gate, sa ilalim ng oxide is depletion region. But wait, you know what happens? As I try to increase yung aking VGS, meron din po na-attract. Papansin niyo po, yung mga charges na nasa source side, which are negative charges, nakikita nila yung positive na nasa gate. So kung ang charges ay negative, nilagyan mo ng positive, ang nangyayari po ay pupunta siya sa ilalim ng gate. So ito mga negative charges na ito, for example, if I try to redraw it, but they're drawn towards the positive gate. So kaya pupunta yan sa ilalim. And then as I increase my VGS, extend yan until matouch niya yung drain. And ano yung na-form? So once na matouch niya yung drain, you create your channel. So how do you now apply? How do you now create a channel kay N-channel MOS? I need a sufficiently large VGS value to create the channel. And when does that happen? When your VGS value is greater than or equal to a certain threshold. So yung minimum voltage to create the bridge between the source and the drain is the threshold voltage. So yung level ng VGS to create a channel is the threshold voltage, minimum, and so on and so forth. So technically, this is called enhancement type MOSFET kasi you need to create or you need to enhance yung channel. And how do you do that for NMOS? You apply a positive gate source voltage to enhance that channel. Now, sir, if you're asking, gaano po kapal itong channel na ito? May approximated thickness yan. It's very thin, 50 to 60 angstroms. Or if you hear of the word angstrom before, ito po ay ganito. Yan yung symbol niya. And that represents 1 times 10 to the negative 10 meter. This is just telling you na napakanipis na channel po niyan. Okay? So, this is how a MOSFET should work. But then again, this is a very simple way to explain it. Marami tayong factors pang titignan. And what are those things that try to change or affect its performance? But then again, it's nice and good to be able to introduce to you yung concept ng VTH. And you need ng positive voltage to create the channel for the NMOS. Okay. So it will always start with a depletion phase before you can say you create the channel or you have the so-called inversion phase. Wait, sir. Bakit biglang nagkaroon ng inversion na word. Napansin niyo po, originally, yung nakapaligid sa ilalim ng gate, dito sa picture A, puro positive yan. Ito mga kulay black. Ano po nangyari nung na-form ko yung channel? Yung channel is now a channel of electrons. And that is negative. Originally, these are holes. And alam natin na ang holes po ay positive. So ano nangyari? So na-form ko yung channel, ang nasa ilalim ng gate ay the channel which is formed by electrons. So from a positive polarity sa ilalim ng gate, naging negative, so you can say that nag-invert yung polarity sa ilalim ng gate. Therefore, you said nagkaroon ka ng inversion phase. Kaya yung channel is also called inversion layer. So this is now called inversion layer. So, it is also important po to note kung gaano kalayo itong channel na ito. So, moving forward, this is how the phases. So, just take note na lang yung depletion phase. So, below the oxide, this is depletion region. And then you have your inversion phase. And these are your, this is your channel already, channel form. Okay. So, moving forward, this is a nice picture to show you yung amount of charges that are being generated for different applied voltages or surface potentials. So, please take note na lang dito yung concept ng strong inversion and weak inversion. Kasi we will use those to define how strong is the channel or how weak is the channel. Specifically po, to define operating conditions ng MOSFET. So, moving forward, and this is what I was trying to refer to. Yung to the right of this plot, ito, which I mean ito, we call it yung output characteristics. Simple lang po yan. Bakit po siya tinawag na output characteristics? Kasi yung output, yung voltage or IV characteristic curve constitute yung output current, which is current from drain to source, and the voltage across drain to source. Kasi for example, if meron kang MOSFET, say for example, meron kang MOSFET, tingnan po natin yung cross-section niyan. Ganito siya. So, ito yung aking gate. Ito yung aking source. Ito yung aking drain. Then, ito ay N+. N+ ito naman ay P. P substrate. So, ngayon, normally, mag-a-apply ka ng voltage across gate to source. So, ito yung VGS. Tapos, mag-apply ka ng, let's say, ang aking source, i-ground ko na lang. Tapos, maglalagay ka ng positive across the drain. We call it VDS. So, ngayon, ang input natin is normally yung ilalagay natin sa gate. So, yung VGS is the input. And then, yung output natin is yung nilalagay natin across drain to source. Kasi po, yung channel is actually flowing from drain to source. So kapag ang tinitingnan ko ay yung dinadaanan ng current, that is from the drain to the source. And that is also your output. Yung input natin is VGS. Yung output natin ay VDS. Kaya, if you talk about output characteristic curve, x-axis is VDS, y-axis is IDS. Ngayon, kung input characteristic curve naman, lalabas na ito ay VGS, ito naman po ay IDS. So ngayon, meron pong 3 regions of operations na we can take note of. For a typical MOSFET, meron po kasing, hatiin po natin. Sa left side ng plot na ito, remember po na yung x-axis ay voltage and y-axis is current. Ito po yan. Mapapansin nyo na if I plot it like this, it seems as though na yung kanyang kulay blue trace parang isang straight slanting line. Ano po palang parameter yung parang may straight response? I mean, ano kayang component yung parang ganito yung kanyang profile? V and I. Tapos ganun yung curve. Very linear. That's actually po a profile of, pag nakakita kayo ng ganito, it's a resistor. Kasi di ba pag sabi na Ohm's law, meron kang V is equal to IR. So pag dinivide yung V over I, lalabas the value of the resistance. So kapag straight line yan, it's actually a resistor. Pag tinignan nyo mabuti, fairly, parang as my voltage increases, my current increases as well. Almost linearly. In fact, somewhere here, napaka-linear niya. Kaya, tinatawag itong region na ito, ohmic. Kasi para siyang resistor. Tinataas yung voltage, tumataas yung current. Now, at some point, mag-saturate yung transistor. Kaya, tinatawag itong saturation region. Bakit siya tinatawag na saturation region? Kasi kahit itaas ko yung voltage, yung current hindi na po tumataas. Kumbaga, saturated. Kahit itaas yung voltage going from left to right of this IV curve, the output characteristics, hindi na po tumataas yung current. As in, stable na lang. Pag ganun na lang siya. Kaya you say that is saturated. Kailan nangyari yung saturation? Kailan nangyari yung ohmic region? There are actually conditions. Now, meron pang isa, if you take closer look sa ilalim, dito, this is when, remember, itong levels na ito ng current are for various gate source voltages. That is increasing VGS. So increasing ang VGS, tumataas ang current level, but what happens is, nagsasaturate. Now, pag tinigyan natin doon sa yung pangalawang level, ito, going down, notice po na masyadong maliit ang current. That's why you call it cutoff region. What does that mean? At this region, ang aking VGS is not enough. It doesn't really create a channel kasi ang VTH was not achieved. Now, kapag na-achieve ko naman ang VTH, pwedeng maging ohmic operation siya na parang resistor o pwede naman para siyang saturated. Ginagamit po itong saturation region, specifically kung gusto kong gamitin yung transistor as a current source. Yan ang magandang application ng transistor na nasa saturation. So, may iba-ibang pangalan pa po itong regions na ito. Yung ohmic po, tawag din dyan ay linear region. Kasi yung IV characteristics niyan ay parang isang straight line. May isa pa pong pangalan yan. If you talk about, di ba kanina po, no? I mentioned na ang channel is also called inversion layer. So itong ohmic region po, you call it also as moderate inversion. And then, yung cut-off naman, since mas mababa yung VGS kay VTH, you can say that cut-off region is also called sub-threshold region. Okay. So cut-off, that is also called sub-threshold region. Or if you talk about yung inversion, it's called weak inversion. Sabihin, wala pa talagang channel or hindi pa gaano karami yung charges na nasa channel. So, wala pang bridge. What about saturation? Ito yung parang napaka-defined na ng channel. Pero to the point na wala na nangyayari kahit increase yung VDS. So, this is your saturation region, is also called strong inversion. Okay. Please note po pala, no? Iba yung sa BJT, iba yung saturation sa BJT, iba rin yung linear region sa BJT with a MOSFET. Okay. So, now we are able to define different regions of operation of MOSFET. And they have different uses, which I will lay down later on. So, perhaps we can try to quickly answer some questions. So does the metal vias form a magnetic field? Yes. Especially po, if you talk about RFIC design. You can mention po na, especially if you utilize very high frequency, nowadays, whenever magpapafabricate ka, pinapacheck na po yung tinatawag nilang antenna coupling. Kasi kung masyadong mataas ang frequency at marami kang metal wires, nakakagawa ka ng antenna. So magra-radiate yan. So you can say crosstalk. So hahalo siya doon sa ibang metal lines. So yes, there's a possible interference with regards to magnetic field. Okay, may Q&A session. So hope this is still very interesting to everybody. So moving forward, threshold voltage, meron siyang parameters. We don't need to detail this a lot. But I want to note po that this is one of the things na designers are considering for threshold voltage is the fact that ito ang profile niya. Ang profile po niyan, kung ang x-axis ay temperature, that is temperature, and this is VTH. Again po, VTH is the minimum gate to source voltage to create a viable channel so that you can have current. But you know, squeal ko rin na even without the channel, you can still have current. We call it sub-threshold current. So that will be revealed very soon. So the profile po of VTH with respect to temperature that IC designers are looking into consideration always is something like this. What does it mean? It means that the VTH has something called CTAT response. Ano po yung CTAT? Ang CTAT po is complementary. We need to be accustomed din sa mga wordings. Complementary to absolute temperature. Ibig sabihin, pag tumataas ang temperature, bumababa yung VTH. Well, there are several dynamics happening doon, lalo na kapag high temperature. You can just imagine, pag masyado mainit na yung device, tendency for the charges to have a lot of energy to move around. Therefore, kahit na you would just need a very small amount of gate source voltage, napaka daming energy ng charges na nasa source. So a small gate source voltage would be necessary if it is operating at high temperature. Kasi yung mga charges, for example, na nasa, I don't know where to draw this. For example, dito na lang. So meron kang source side, so ito yung aking source. And then papapuntahin natin siya sa aking drain para maging close ang circuit. So meron kang gate dito. At dahil napakataas na ng temp, yung mga charges dito, let's say mga electrons dito, have a lot of energy. Naiinitan sila eh. And as a result, they will have a lot of energy. So very small, fairly smaller gate to source voltage can readily pull them to here, to there. Because they have energy. So tendency, as you increase the temperature, the amount of VGS needed to have a channel is lower to achieve a channel. So this is critical whenever you want to design circuits. Ngayon, kung dinala mo naman yung circuit sa North Pole, assuming hindi pa masyadong talamak yung effect ng climate change, the tendency for your circuit is really to shut down. Kasi napakataas ng VTH. If you're asking po, no, what is the range of temperature that we are considering in the design? So, way back mga 3 years ago po, they are looking at temperature range from -40 to 125 degrees. If you're asking po, well, is this a safe margin still to operate? Yes. This temperature range is still away from the melting point of silicon. So this is still safe, but then you need to be careful. You can have a lot of current even if you don't have VGS. Kasi threshold. Okay. So the threshold voltage has a CTAT response or negative temperature coefficient. That if you increase the temperature, the VTH goes down. Okay, so these are the different operating conditions. They're actually defined of the VGS and the VDS. Okay, so VGS is still 0. Even if you try to have a VDS, wala pa rin pong channel. Pero ano yung nangyayari? Kumakapal po yung depletion region, which is actually dangerous. What I mean? So ganito po siya. If I try to draw yung transistor again, very quickly, it's like this. Tapos meron po siya dito. And then, meron po siyang N plus dyan. Tapos N plus dito. Tapos, meron akong ilalagay na gate source voltage. Let's say ganito. Tapos naka-ground lang siya. This is a VDS. remember po na, for example, dito ko na lang po ilalagay yung terminal na yan, P plus, to connect to my P substrate, naka-ground yan. Ito yung P substrate. So even if, for example, ito yung drain, at ito yung source, let's say naka-ground lang yung source, naka-ground din yung gate, wala pa akong nilalagay dyan, what happens po ay, meron kang reverse biased PN junction. Anong PN junction po yun? Yung N diffusion, tsaka yung P substrate. So, as I increase my VDS, naka-reverse bias po yung PN junction formed by my P substrate and my N diffusion. What happens is, parang ganito siya. So, ito yung aking P substrate, P sub, and then this is my N diffusion, which is my drain. Ito yung drain. So, what happens po ay, naka-reverse bias yan. So, kumakapal yung depletion region. So, kumakapal yung depletion region. Actually po, nako-compute din kung gaano ka-wide itong depletion region. Depends on several parameters like doping level noong substrate, and so on and so forth, and even temperature and voltage. So, what happens? So, kaya po, kumakapal na kumakapal yung depletion region ng drain to the substrate region. Yan. Kumakapal yan. Delikado po yan. Kapag masyado nang mataas yung VDS at nag-overlap, so sumobra yung depletion region, nag-overlap ng ganito, ano na po mangyayari dyan? Again, ito po ay depletion region. This is catastrophic. So you cannot just put a lot of VDS. What happens is, papasok na yung depletion region sa source. Di po ba, kapag depletion region, yung aking majority carriers ay hindi makakadaan. Pero meron kang tinatawag nilang reverse saturation current. Di po ba ito yung if I remember it right, meron kang diode current, tapos meron kang IS, tapos meron kang parameter E, tapos I kind of forgot, we have, I think, negative K, tapos VT, something like this. But the point is, meron ka nitong IS, so please verify na lang for the students, ano yung other terms dito. Ito yung reverse saturation current or IS. What it means is, ito yung minority carrier flow. And di po ba, kapag naka-reverse bias ka, yung majority carriers hindi magpo-flow. Pero yung minority carriers, sila ngayon yung sikat. Right? Sila ngayon yung magpo-flow dito. Ito yung IS. Ngayon, kung magpo-flow yan, parang lalabas na magkakaroon ka na ng current. Kahit wala ka pa talagang channel. Dahil po, nag-merge yung depletion region. In-overlap ni depletion yung sa source. So, kaya dapat, you cannot operate the transistor to very high VDS lang. May limits po yan. Now, ngayon, kapag that is for wala pang channel pero nag-thick yan yung depletion region. Kapag meron ka nang in-apply na VGS pero mas mababa pa sa threshold, you say that it's called sub-threshold region. So, wala pang channel or wala pang sufficient channel, But you are now initiating na magkaroon na itong channel na ito. But, here's the thing. Itong subthreshold current, let's say IDS in subthreshold, sub-VTH is not really equal to 0. Kahit na wala ka pa talagang channel o hindi pa kompleto yung channel, hindi siya 0. In fact, itong IDS po is a strong function of the temperature. As I remember, that is even exponential. So, kahit wala ka pang nilalagay or insufficient pa yung VGS to create the channel, pag tinataasan yung temperature, you tend to have even current, even if it is still no channel. Because the subthreshold current is actually a very strong function of temperature or VT or the thermal voltage. So it's going to be very strong function. In fact, that is a exponential function. So may current pa rin. Now, in real design po, ginagamit itong subthreshold current. Nowadays po, you will, I think, may it be still in the research phase, I was able to see po yung, let's say, op-amps na ang power dissipation ay nanowatts. Why is it so? Definitely, you cannot just pull down the voltage. What you can do, remember po, if you talk about power dissipation is actually equal to VDD times the current. So if you cannot reduce VDD, what you can do is really pull down the current. And what if you are operating in subthreshold, where the current po ay ranging from maybe a couple of 100 picoamps to just around maybe less than 10 nanoamperes. That's a very low amount of current. Kaya, nowadays po, subthreshold MOSFETs are actually being used to develop power-efficient circuits because they will now dissipate very or ultra-low power ultra-low powers. At ginagamit po yan. If you're asking po, where will they use it? For example, gagawa ka ng circuit to connect or to harvest some signals from the brain, pero implanted. Well, you would rather use subthreshold MOSFETs na hindi masyadong kakain ng current, hindi siya masyadong iinit kasi delikado po, no? Lalo na kung implanted yan sa brain, you don't want it to be eating a lot of current. Kasi iinit yun. And that could be catastrophic for the person. Kaya subthreshold, well, it's being used specifically to develop circuits na implantable that technically does not dissipate a lot of current or close to no current at all. That is in the analog domain. Sa digital, you hate this. Okay, so now, kung meron ka ng VGS na fairly higher than or equal to VTH, pero yung VDS is less than the difference of the two, you call it linear. May tawag po pala dito sa, let's say, na-hire ka sa isang IC design company at dumadami na po yan ngayon. Okay? So, in Manila, dumadami na rin siya, no? And some branches are opening up in other parts of the Philippines, of the country. Meron pong term for VGS minus VTH. And you call that VOV. And that is called overdrive voltage. Okay. Ngayon, kanina po, I was trying to show you a plot like this. We try to look back doon sa output characteristics niya. You have VDS and you have IDS dito. If I try to again show po yung plot ng curves na ganito. Okay, so okay. And then I try to interpolate yung mga points before the saturation. Ano kaya itong mga values na ito? Itong mga values na ito, yung dotted lines, yung values na yan, that is your VOV. And that is given by VGS minus VTH. Kasi po, whenever you exceed itong mga VOV values na ito ng VDS, itong mga values na ito, if you go beyond it, what do you notice? You actually are now operating you're operating in saturation. Okay, you need to overcome the VOV or the VGS minus VTH to achieve the next operating condition called saturation. And you know what po? Itong VGS minus VTH, may isa pa pong pangalan. Aside from overdrive voltage na ginagamit sa industriya, you call it drain to source sat voltage. Saturation voltage. Or you can say this is your VDSAT. So VDSAT is equal to VOV, and that is the VGS minus VTH. So, kapag meron ka na pong sufficient na threshold voltage, I mean, si VGS is equal or a little bit greater than the threshold voltage, then yung extent of the VDS naman, greater than or equal to the overdrive voltage, which is the difference of VGS minus VTH, will define your transistor to be operating in saturation and the other one to be operating in linear mode. Okay. Now, I want to mention na meron pong dalawang klase ng field. Meron pong isa, we call it horizontal field, at meron din pong isa which we call vertical field. Bakit po meron dalawang electric field na involved? Remember po, ang electric field by definition ay voltage over distance. So pag may voltage at one point and there is some insulation, you have an electric field. Okay? So you have two types, the horizontal and the vertical. Now, if you're asking po, okay, so big deal, sir. No, so what? That's actually a nice question. You don't want na itong horizontal field will dominate the vertical field. What you want is, often, itong vertical field should be greater than the horizontal field. Okay, so why is it so? Kasi po, remember, dapat yung pag-control ng channel ay based sa VGS. Ayaw mo na based sa VDS. Kasi po, technically speaking, ang gumagawa ng channel ay si VGS. Si VDS, parang yung kanina, wala kang VGS, so, sa situation A, tinataas yung VDS, anong mangyayari? Kumakapal na kumakapal yung depletion region until such time na magkakaroon ka ng reverse saturation current kahit wala pang channel, may current na, kaya lang minority carriers. Which is actually going to be called leakage current. So dapat ang gagawa po kasi ng channel ay si gate to source voltage. Third question, why is it called vertical field? Actually, simple lang po. If I try to draw dito, yung MOSFET, so for example, NMOS na lang po. Tapos, let's say, gaground ko siya. Tapos, maglalagay po ako ng voltage dito. Ito ay VGS. Ito ay VDS. VDS po siya, and then VGS itong isa. So let's say, dito ko na lang po ilalagay yung bulk. For example, P+, naka-ground. Remember po na ito yung oxide at may thickness po siya, TOX. Tapos ito naman po ay may distance na L. So ngayon, ito po again yung gate. Ito yung source, ito yung drain. Yung electric field ko na vertical, literally is actually vertical. Pag ganun siya. Ito yung aking electric field na vertical that allows you to invite charges from the source to go towards the drain below the gate. Isa naman po is horizontal. Ito naman yung due to the VDS, pag ganun siya. Ito naman yung horizontal field. Now, again, dapat ang main actor is VGS, hindi si VDS. Kasi si VGS lang yung nakakagawa ng channel. And again, yung channel is kumbaga, the name of the game po is to create a bridge between source and drain. And you can only do that if you use VGS. Otherwise, if it is not based on the channel, then you can say that leakage current yun. Any current not due to the channel is considered leakage current. So it has to be via the channel. Otherwise, leakage current siya. So ngayon, by definition again, yung electric field is voltage over distance. This is actually going to be quite critical kasi if you talk about the vertical field, it is the VGS over how thick is the oxide. Whereas yung horizontal field is VDS over how far is this length. Now, let's say na itong VDS and VGS have the maximum value possible. And that maximum value po is, let's say, VGS, for example, is equal to VDS. Ito ngayon ay yung supply voltage, VDD. Ito yung highest voltage possible in any circuit. Yung nilagay nating battery. So ngayon, lalabas na vertical field is equal to VDD over oxide thickness. And then, yung horizontal field naman is VDD over the length. And if you talk about L being the minimum channel length, now, you have a situation dito. Dapat, the vertical field should exceed the horizontal field. Should be greater. How will you do that? Dapat, yung 1 over TOX should be greater than 1/L min. Make sense po yan? So ngayon, I cannot just reduce L min. So let's say if I try to reduce the minimum channel length, well, if I reduce this, si L min, as a result, itong aking factor na ito will increase kasi yung denominator niya is going down. So entirely, this will go up. So now I'm gonna be forced to reduce my oxide thickness. So I can now reduce my oxide thickness para itong full factor nito, 1/the oxide thickness will go up. And here's the situation. If I try to reduce the oxide thickness too much, I can actually break etong oxide sa gitna. Meron po kasi yung breakdown field. Ito yung, pag let's say punta ka ng computer shop, tapos maglalagay ka ng processor doon, dapat meron ka anti-static. Kasi pwede siyang masira by static. At when they say masira, the one that is actually broken is the oxide ng MOSFET. And this oxide is very thin. As I remember, depending on technology, the thickness of the oxide could just be around 100 angstroms. And that is 100 times 10 to the negative 10 meters. That's very thin. So, I cannot shrink my oxide too much para yung vertical field would exceed always my horizontal field kasi napaka-aggressive ko to make my transistor very small. They do have the same voltage. So I can maximize it by VDD. So what will happen? So I need to change itong oxide. Kasi for silicon dioxide, there is a breakdown field. The breakdown field is just around 5 mega electron volts. So I need to find a material na I can shrink the oxide thickness, but without trying to break the material itself. And I will show that later on. Meron na pong napiling material, and they call it hafnium oxide. Now, if the minimum length is too small, excuse me, the horizontal field will be very large. So if the situation po is horizontal field exceeding the vertical field, you call it leakage current. Magkakaroon ka ng leakage. And why is that so? When does it happen? Remember, dito sa diagram na unang-una nating pinakita on this slide, pag masyado mataas ang VDS, there is a tendency for the depletion region to try to get so close to the source para may daanan na leakage current, which is etong reverse saturation current. Current due to the minority carriers. So that's a big no-no na you have an extra large horizontal field. So therefore, you cannot just reduce the length that much. Or what you can do is, while you reduce the length, you reduce the thickness of the oxide para parating greater si vertical kaysa kay horizontal to avoid leakage current. And that leakage current is also referred to as subthreshold current in some cases. So, moving forward, but the near VTH, I mean, if you operate your circuit very near the VTH, which is dangerous, it actually gives you a lot of benefits as well. It gives you a very nice trade-off between amount of energy, because even in IC design, you want at best your circuit utilizing not too much energy. Kasi you want it for a long term. let's say for chronic application, you don't want it to be just eating up energy or power. Therefore, you need to reduce its energy per operation. And that is provided for you by operating very near the threshold voltage. So notice po na these are three regions: sub VTH, near VTH, and super VTH. So in these super VTH regions, you're now in saturation, or you're now in linear region. So we don't really care about that. If you try to operate on near VTH, you tend to have a fairly low energy per operation, around this much, around here. And then, but I cannot just operate it in near VTA, sub VTH, because mataas naman yung delay. Babagal yung circuit. Kasi po, normally, ang speed ng circuit depends upon yung current na kaya niyang isupply. So, kung masyadong mababa yung current dahil wala ka pa talagang channel or very close to VTH ka, tendency is, or sub-VTH, masyadong maliit yung current, kaya mabagal yung circuit. Kaya kung papansin nyo, if you are operating in saturation or linear, ang delay mo is actually around 1,000 times less because your circuit is faster. Kaya lang, please remember po na whenever the circuit is said to be faster, it will dissipate the more current. Kaya meron pong trade-off. I mean, you cannot really have a very fast circuit na walang dinidissipate na current or mababa yung current dissipation or low power. A very fast circuit tends to dissipate more power because it needs more current. Current for what? Current needed to charge a capacitor. Okay, so I will introduce that in a short while. So, kung titignan niyo po yan, designers now see na if I try to work on near VTH, well, I have a fairly low energy per operation, and at the same time, I have a fairly low delay. So that's the beauty of operating in near VTH. But what is the problem? Perhaps a little raise in temperature can actually pull you from near VTH to sub VTH. And what will happen po ay super bagal ng circuit. By the way, y-axis here is delay. So those are payoffs. I want to mention po what speed is all about. Ganito po kasi yan. Speed is all about how fast am I able to charge the capacitor. Higher current tends for me to charge the capacitor at a faster rate than a lower current. So you see that in a short while. Okay, so in actual design, you have some model parameters. Maraming klase po yan. Meron po yung EKV, meron naman po yung mas ginagamit in industry, yung BSIM model, which is developed in UC Berkeley. So what are these model parameters? Of course, we cannot just calculate by hand yung mga current, yung mga voltage, yung mga power sa isang circuit. I can do that if I'm just using something called level 1, which is very, very fundamental. It only needs a couple of parameters like VTH, lambda, KP, gamma, and they offer for you a good approximation kapag length mo ay greater than 10 micrometers. Well, this length is actually good, but not for digital. This is good for analog. Okay, so analog design, this is quite good. but not for digital. So, because as we speak, if you want to have very short channel devices, especially to talk about digital implementations, then you need more parameters to predict its performance. Kasi some of these are actually quantum level na. So they tend to jump off to a higher energy level, therefore creating current and so on and so forth. Very hard to predict. And you need to add more parameters so that you can have a more reliable simulation result. So normally, what they do is incorporate the model parameters such as this from the foundry, run it through a simulator called SPICE. Usually po SPICE yung ginagamit, which stands for Simulation Program for Integrated Circuit Emphasis. And then they know these parameters, and then they try to compute for you the current, the voltages, and so on and so forth. Okay, so moving forward, so the smaller the transistor, the harder it is to model. So there are other factors affecting its current. Now, here is a very simple expression to define a level 1 current ng MOSFET. And by the way, this is the current in saturation. Saturation current. Okay, so you have the parameters Kp, and Kp po is mobility ng charge carrier times the unit oxide capacitance. It's called transconductance factor. And then, so you can write Kp being equal to mobility times COX. And COX is the unit capacitance per unit area. Or you can write it like this. Permittivity of oxide over the thickness of the oxide. And then you have your VGS, VTH squared. So, you might be wondering po, saan nanggaling yung squared? Sometimes, itong equation na ito, they call it the square law model. So, this is called square law model. Ganito po kasi talaga yung nangyayari dyan. Okay, so let me find po clean. Wait, dito na lang. If you try po to look into yung IV characteristic curve, so for example po, this is VDS and this is IDS. Ang itsura po niya would look something like this. Let's use one color. Okay, so technically ganito siya. Tapos magka-curve yan, tapos saturate. Pero in reality po, yung equation is telling us of a parabola. Kasi naka-squared. So actually, the equation is telling us na ganito. This is what the square law is telling us in color green. Kasi naka-parabola ito eh. Squared. Pero in reality, at this point, nagsasaturate na po siya. So, hindi na magbabago yung current. Okay, so, this is the equation, yung kulay green, represented by this. Kaya lang, once na na-reach physically, na-reach na nung transistor saturation, hindi na magbabago yung current. I mean, the current through it is the same. Kaya nga, tinawag sa kanya ay saturated. Okay. But the current at this point, ito may cross dyan is defined by this equation. Now here you can define some key parameters po, yung lambda, yung threshold voltage, and Kp. Okay, so moving forward. When you talk about fabricating the transistor, for example po, you have this kind of current. I mentioned this current, this form. This is again po yung square law model kasi meron square doon. The transistor itself, meron pong tinatawag na corner cases. Let's say, magpa-fabricate yung semiconductor foundry ng isang transistor lang and then kakabitan niya ng capacitor. Parang pong yung nasa baba. So ngayon, itong transistor na to, let's call it M1. Pwedeng yung current na ipoproduce nito defined by ID is larger than the normal. Ano mangyayari po kapag yung current na na-produce niya is larger than the normal? For example po, I'm trying to charge itong CL and lumabas na plot is something like this. And itong kulay red is the nominal case. Or you can say this is the typical case. Typical. So, pag yung transistor is said to be providing for you a current that is higher than typical, what happens is, yung pag-charge ng capacitor will be faster. I mean, kasi remember, pag nag-charge ka po ng capacitor, it tends to copy when it is fully charged yung input voltage. In this case, this is the input. So now, if it reaches Vin, then you say that the capacitor is fully charged. But there's a time at which the capacitor will charge. So notice po that if you have more current, then you tend to charge the capacitor at a faster rate. Kaya lalabas po yung fast charging chargers tend to have higher current outputs. Kaya yung phone mo tends to charge faster. So they have a higher current. A smaller time, charging time, let's say T sub 1 as compared to that nominal. Now, if you look at the parameters involved in trying to define po yung current, you have the K or Kp, you have the W over L or aspect ratio, you have the threshold, and you have the lambda. So if it is providing a fairly higher current for the same W over L, you might as well figure out na, well, the MOSFET seems to have a smaller VTH. Kasi if this parameter VTH is smaller, your ID, kasi nakasubtract yan, ID tends to be higher. Right? So if you look at it here on the plot, this is actually giving you the design space where your transistor could operate. So if your transistor is giving more current than the usual, it is said to be a fast transistor. That's why noted here, fast MOS transistor tend to have higher current than the typical. Other aspects, yung mobility niya is fairly higher than the typical. Kasi remember, K is actually mobility times COX. So on the typical case, if it is a fast case, the transistor gives more current than usual. Therefore, it could be the effect of mobility, or the threshold voltage is smaller, or its width is bigger than the typical, or the length is smaller than the typical. Or if I try to expand itong mobility factor in COX, that is, EOX over TOX. So it only means that TOX is smaller than the typical. All of these add up to have to a higher current for a fast case or fast NMOS. And the reverse, if you reverse all of these situation, you have the slow transistor. Kapag slow naman, mas mabagal siya mag-charge kaysa sa typical because this is now yung typical slow case and the other one is the fast case. So you take more time to charge a capacitor. And that translates to smaller current. That would mean, see, for a slow transistor, mas mataas yung kanyang VTH because itong subtrahend is higher. Other factors could be slower mobility. Pag na-fabricate, mas makapal yung oxide thickness, and so on and so forth. It's all about, itong speed ng transistor is all about the current driving ability. So kung lalabas na mas mababa yung current output niya, because it is maybe because of higher VTH, you can say that that is a slow transistor. And so you have typically for MOS libraries provided for you from Foundry, they will give you the 5 corner cases. Kasi they define 1, 2, 3, 4, and then typical case. These are your corner cases. And also, sometimes they will even add you Monte Carlo situation. Monte Carlo models. So all of them provided for you by the one who will fabricate the technology or your circuit. Okay, so moving forward. Now, this is something na I was saying kanina na everything below the VTH, this is the VTH. So I try to go lower than the VTH. This is gate voltage. I suppose we should not have any current. I mean, this had to be sub VTH. But guess what po? You do have some current. Kapag ginawa kong log scale, I have this profile. I have this graph. Now, para siyang straight line pag naka-log scale. You call it, kapag kumuha ako ng slope dito, well, that is called SS. That stands for sub-threshold slope. So, if I may ask, although I will not ask anybody for a poll on this, if I try to have 2 devices, let's say, ito yung VGS, tapos ito yung IDS, again, you will not see the current in linear scale. Gawin po nating log scale. I mean, by tens or hundreds yung factors going up. Then I have the following. I have 2 plots. So I have like this. Let's say I have M1. And then meron din akong isa pa. M2. Ito yung kanyang input characteristics. Where is the VTH? It's here. I'll teach you po where the industry obtains the VTH. How do they get it? So, if you are to choose who is a better transistor, let's say magde-design ako ng switch or sa digital ako titingin. Ayoko na analog. I would say M1 is a better transistor than M2. So, okay, so I'll choose M1. It has a better swing. It has a better sub-threshold slope. Actually po, if you have a lot of area going around from your VTH to your lower than your VTH, you have a lot of problem dito. Kapag yung sub-threshold slope or SS is low, then itong transistor na to tends to leak. So M2 tends to have more leakage current. This is actually a leaky transistor. I don't want this. I want a swing or a sub-threshold slope na very, very high value. So I want a sub-threshold slope, or I'd rather choose M1 than M2 because the slope na itong curve na ito is higher than kay M2 or more vertical. Now, in industry, they try to reverse itong sub-threshold slope to define a certain parameter called swing. And that is 1 over SS. So, kung gusto natin na itong plot nito, log scale, is more vertical, like this, that would be better. Now, if I try to reverse itong sub-threshold slope to define the so-called swing, then ang gusto natin, kung masyado mataas ang sub-threshold slope, so lalabas, mababa ang swing. Gusto natin lower swing. Pero of course, it has to be less than 60 millivolts per decade. Saan po galing, sir, itong 60 millivolts? Actually po, that comes from this. So yung swing is, if you see KT over Q, simplihan po natin yan, that is called thermal voltage. Okay? And then, ln of 10, if you try to operate using this equation, now, here's the thing. I want you all to remember po. Ano po itong kulay green sa baba? Itong MOSFET. This is depletion region. Now, depletion region, pag tinigyan natin po itong structure ng MOSFET na ganito, meron akong makukuhang dalawang capacitors. Isang COX at isang C depletion. So ngayon po, notice po na nakamultiply yung thermal voltage times ln of 10 with 1 plus the depletion capacitance sa COX. So I don't want a depletion cap. Kasi lalabas, yung swing tends to be higher. And if it is higher, ano nangyari sa sub-threshold slope? The sub-threshold slope, SS po pala ito, tends to be lower and makes it more leakage. What constitutes the leakage? It's because of the depletion capacitance. So long as there's a depletion region, and if it is higher, then you have more leakage coming into the picture. Okay. So this is all about swing and what industry is looking into. We talk about how good is the transistor in terms of leakage. Okay, so moving forward, speed is related to how much current being provided to drive a capacitor. Another aspect is, kasi if you again take a look at the current equation, you have IDS, which is a function of Kp, And you know that Kp is actually equal to mobility times COX, unit capacitance of the oxide. So it's just like saying IDS is actually proportional to mobility. So it is actually affecting also. So kung yung current relates also, so higher current tends to charge the capacitor at a faster rate, it's also trying to relate to you the resulting frequency. So the maximum frequency of a transistor, if you want to use it for RF or wireless application, is actually proportional to its mobility over the minimum channel length. So kaya po, they try to reduce the channel length so that you can operate on a higher frequency. That's why they want to scale it down. Pero see, you have another factor po that you can improve on, and that is mobility. Okay, so what is technology trying to do to increase the mobility? Simple lang po, they want to make the space between the atoms wider. That's why from silicon, nag-migrate to silicon germanium, compound semiconductor, then now strained silicon. This is towards increasing mobility. Bakit po kailangan increase the mobility? Wow, you can have more current, faster transistor, or higher frequency. Okay, so what does it mean to increase more mobility? Stretch it. Kaya strained it. Stretch or strain it. So notice that silicon and strained silicon, mas malayo yung distance between the atoms. So parang mas maluwag kung if you talk about traffic, mas maraming space to move around kapag strained silicon as compared to silicon. Kasi the charge itself would tend to hit a lot of these atoms even before going from one point to the other. So lesser friction, faster transistor. So kaya they're looking at strained silicon. Now, so this is Moore's law. Number of transistors on a chip doubles for every 18 months. You see the explosion of the number of devices. What does it mean to have more devices there? It implies that you have more functionality. See that this is functionality. There's an explosion of functionalities being done as you try to increase the number of transistors. And then, because there are too much transistors on a specific area, you tend to reduce the cost per transistor. So, bumababa ang cost while you have more functionality. I mean, cost per transistor. And then, what it means is, as you increase the number of transistors, yung kanyang operating frequency, which is a function of its speed, telling you about its speed, is rising. Tumataas yung speed kapag lumiliit yung transistor. Bakit po ganon? Kasi if you look at the cross-section of a transistor, it looks like this. Alam niyo po, isang bagay na maganda rin pong tandaan, let's say, meron kang depletion region. Tapos, nilagyan ko siya ng, let's say this, sorry. Okay, so if, for example, this is P and N, tapos talagyan ko siya ng reverse bias, di po ba kakapal yung depletion region? Kakapal yan. So yung tinatawag nilang depletion width is gonna be wider. Pero remember na as you try to widen this, the depletion region actually behaves like a capacitor. Meron siyang tinatawag na depletion capacitance. And the depletion capacitance value is actually, for example, that has to be the area of the cross-sectional area of this section of the diode times the permittivity divided by the depletion width. So wider depletion width, so you increase the depletion width, your depletion capacitance decreases. Kaya po, if you remember, meron mga diodes you call varactors. In fact, meron yang capacitor dyan, and that is due to the depletion capacitance. So every time na may p-n junction ka pala, you actually create depletion capacitances. So maraming capacitances po yan. You have capacitances going, since may depletion region ito, at may depletion region din itong isa. So meron kang capacitances going from here to there, here to there. Also capacitance going to here, capacitance to here, capacitance to here. All of these capacitors, yung mga C na yan, those are proportional to the width times the length of the transistor. And if you try to make that transistor smaller and smaller, you tend to make the width and length smaller and smaller. You tend to have lower capacitance. And if you remember po that the cutoff frequency, transit frequency, they call it transit frequency, that is inversely proportional to the overall capacitance. So smaller capacitance, faster transistor. So that's the essence. So pag mas maliit ang transistor, yung mga parasitic capacitances, which I highlighted dito, yung mga C na yan, tend to be smaller. Therefore, your transistor tend to be faster or can operate at a higher frequency. Okay, so, but then again, the problem is, if you have more of these devices, pero these devices tend to leak out current, and you have a billion of these devices, for example, a transistor that is technically off, let's say may VGS akong 0 lang. Tapos, nagkaroon siya ng current, let's say 1 nanoampere. Then I have a chip consisting of 100 billion of these transistors. What happens? If I try, and then over the area na 1 cm squared area. So, walang voltage, walang channel, pero may current. So 1 nanoampere, lahat sila naka-off, times 100 billion gives you 100 watts. And then power density over current, power density 100 watts over, for a VDD of, let's say 1 volt. So you have 100 watts over square meter. And that is very close to the heat generated by a nuclear reactor. So kumbaga, the circuits themselves are stagnant technically, but because of the leakage current that happens dahil masyadong maliit yung distance ng source and drain, because of the horizontal field, because of the very small channel length, so you have a lot of leakage, and that could account for a very high power dissipation kahit na standby lang yung circuit. That is why you have several approaches to remove the power dissipation issue, the leakage current. The scaling down limits, just mag-wrap time. You see, this was predicted long time ago by ITRS, and they are an institution that are trying to make predictions or analyze what would be the next trend in IC design. So the prediction then was 10 nanometer, that's it. No one will go smaller than 10 nanometers. So we need to change the topology already. Not yung mga transistors that we have been talking about kanina, we call it planar. I mean, isang area lang siya. Planar type. The idea then now is to go 3-dimension. So 3-dimension po could consist of yung ginagamit sa PlayStation before, FinFET, or sometimes they use a fully depleted silicon on insulator, or sometimes we will call this FDSOI. So gumagamit ng insulation below, or gagamit ng nanowires, or a monolithic 3-dimensional transistor. This trend has already been broken. TSMC has went for 5 nanometers. They released 7 nanometers already, but don't worry, because up until recently, IBM created the way. They created 2 nanometers. But the device is not anymore the planar transistor, but rather gumagamit siya ng nanosheets with the advent of carbon nanotubes. So the smallest by far is 2 nanometers. So yung more slow po kasi, it's more of digital. Kaya napansin nyo, yung scaling ng Moore's law or nag-increase the number of transistors, they are actually being related to speed ng processor, gaano kagaling yung processor, or gaano kataas yung memory. Now, when you see the slide kanina showing a comparison of the power density of typical devices or even yung rocket ship, so nagiging comparable sila. Now, naisip na iba, okay, so let's do away with all of these digital approaches for Moore's law. Let us operate on something called more than more. And more than more, or beyond more, it's the name of the game is diversification. Kaya po, hindi lang puro mga digital components like mga logic gates or some registers, pinasok na rin yung paggamit ng analog components like op-amps, or more commonly, operational transconductance amplifiers. Meron din diyang filters, okay, or you can say op-amps, and so on and so forth. And then, meron din siyang nilalagay na passives. Pag sinabi pong passives, ito yung resistors, capacitors, and voltage application. Or yung mga accelerometers that are the main reasons why we can change yung orientation ng ating cell phones using MEMS, and recently biochips. So because of these, all of these components added all together, you create something called system on chip, or even LOC, lab on a chip. May sensors na kasi involved, even some biochips. So the idea is of more than more is, let's do away with digital. Let's add more functionality instead while we're trying to scale down. And for that matter, meron ka mga op-amps na nade-design in tandem with the passive components and even sensors and actuators or transducers in the form of MEMS to create a full system. And that is a direction nowadays. So hindi lang siya microcontroller lang, may component dyan na may amplifiers, may mga references, and so on and so forth. So this is the idea of, maybe I can just very quickly run down yung what are the techniques being done to address the issue of scaling. Okay, so moving forward, well, the idea is we need to learn from nature. You see, from the left side, the human brain is 20 watts, dissipating 20 watts approximately, and it is 3-dimension. Consists of 100 billion neural cells, equivalent to 1 trillion transistors. But we are still very far. Yung ating fastest processor is 2-dimension, 200 watts, only 3 billion logic transistors. So we need to somewhat emulate the brain. What are opportunities for all of us? Well, nowadays, they are looking into changes in the standard approaches to develop the transistor. So they replace the bulk, they put some silicon on insulator, may oxide sa ilalim, or they even use strained silicon to make it faster. Yung isolation, LOCOS is local oxidation of silicon. Pinalitan ng shallow trench to save area. And naglagay ng more wells, naging triple well para magkaroon ng more shielding. They use high K dielectric para I can make my thickness of the oxide even smaller. They change the profile of the channel from retrograde to halo. And they even try to change the infrastructure. Planar, yung pinapakita nating example, ginawa nilang triple gate, ginawa nilang FinFET. Okay, so just to show you na ito yung ginagawa nating analysis kanina, it's called bulk. Naglagay sila ng buried oxide, naging silicon on insulator. Protected ngayon yung ilalim. And by doing so, wala ka ng substrate current. So nabawasan yung substrate current, therefore, less leaky. And what they do is even add a buried gate. So meron kang gate dito sa ilalim to create 1 and 2 transistors and you save area. And more so, they do vertical MOSFET to create 1, 2, nakaikot kasi ito, no? So you have 4 transistors over the same area. And that is the essence of, so they change also your material, so they can, now it's hafnium oxide or even zirconium oxide, so that they can even shrink the thickness of the channel of the oxide without breaking it. Kasi merong maximum breaking point yung silicon dioxide. And then, okay, sorry, marami pang to share, no? I prepared 200 slides pala. No? So this is the situation. Just please remember po yung leakage path. And itong mga blue traces na ito is your depletion region. So you don't want them to overlap kasi magkakaroon na leakage path. So how do they try to block this? They added yung APT, anti-punch through implant. They added pocket implants. And then yung parang kanta ni Beyonce, you have halo implants. Why is it so? So they have additional implants ito para yung subthreshold current will be technically reduced so they cannot go here. So yung current na yan is actually very close to 0. So it's more like this. And if you want to save on area, so this is the new transistor. Marami siyang nilagay pocket implants, additional wells, lightly doped drains, anti-punch implants, or they change the topology. They utilize 3 transistors on one area. If you're asking po, where are the transistors? You have 1 here, you have another here, and then sa kabilang side. So you have 1, 2, 3 transistors for the same area. How do they do that po? They go all the way vertical. And this is FinFET, and this is pretty old. Ginamit na po yan sa PlayStation. And then they do this, or else. So gate all around. So notice na meron kang 2 slabs of material. Then pinaikutan ng gate material. So you have 1 transistor here, transistor here, transistor here, transistor here, and so on and so forth. So you have a lot of transistors while you are trying to consume the same area. This is done in Korea. And other stuff, they did nanotube and nanowires because of carbon nanotubes. And so, maninipis yan that can go towards 1 nanometer. So, carbon nanotubes, very stiff, very strong material, doesn't really break. And so, you have 1, 2, 3 transistors that are created because they are very thin. And then you have graphene transistor, similar concept to nanotubes. And MEMS, actually, the only way to really remove the leakage is physically take it out using a relay. So, without a voltage, walang connection itong dalawa. With a voltage, they are connected. So, they dissipate no power. Problem po ay area. Medyo malaki yung consumption ng area nito. And next things will be the self-healing transistor. This will give us a leverage to go to space where components tend to be broken because of the cosmic radiation. So what this does is, kapag tinamaan ng radiation from the space, mag-heat up itong aking gate. And by heating up, if you remember yung sinabi kong annealing kanina, it will try to fix itself. So, lahat ng mga broken bonds are bonded together again. So now we can even go to space with a good enough or more confidence without it being broken. So I do have a lot of topics to cover, perhaps hopefully by next time. And just want to show a slide like this. Part of the journey is the end. Thank you so much po, and hope if you have questions na hindi natin na-cover, you feel free po to email. Apologies po for medyo na late. May questions po tayo?
Okay. Good afternoon. Sir Doc Mikey, right now, we have only captured one question via the YouTube channel, YouTube Live. And the question goes like this. It's from Miss Mariela. In power MOSFETs, why is it important to keep the RDEs on low? Again, in power MOSFETs, why is it important to keep the RDS on low?
Thank you for that question. Because ma'am, I can try to write dito ma'am on this slide, sorry.
Okay.
Okay, I have a blank slide na lang po. Yung power MOSFET is normally ginagamit po siya for a component called LDO. LDO would stand for low dropout regulator. Ito po yung component, basta regulator siya. And please do keep in mind yung word na dropout. Okay. So, ang ibig sabihin lang po nun, ang structure niya would look like this. Meron kang PMOS dito, tapos meron kang supply voltage, tapos, if I remember, positive, if I'm not mistaken po, no? Ganito siya. Oh, wait. Dapat positive ito, and then this is negative. Sorry. Then you have the feedback. And then, meron kang, meron kaya mga resistor dito. And then, your output is somewhere here. Tapos, meron kang nilalagay na load dito. Okay. So, ang idea po kasi meron kang band gap voltage dito, constant, a dependable voltage source. Gusto natin, ang essence po kasi ng low dropout is such that I will supply I can supply the target current and at the same time provide a suitable V out dito. Ngayon, if we want to push further, if we want to really go close kay VDD for my V out, we have a situation. If you want to go close to VDD, the problem is, itong transistor na ito, will definitely have an RDS on. Problem po if kung medyo mataas yung current mo dito, let's say I load, depende sa rating. So nangyari po ay magkakaroon siya ng current, and pag may current, may resistance, tendency is magkakaroon ka ng voltage. So may resistor ito, and that is RDS on, magkakaroon po siya ng voltage drop. Ang tawag po dun sa voltage drop, or magkakaroon ka ng something called dropout region. So, yung Vout mo is not gonna be very much equal to VDD, but Vout tends to be a little less than VDD. And that is because of the RDS on. So you want to reduce RDS on, and to do that, you'll be surprised po na this transistor is gonna be very, very wide. This pass element. So kaya they just want to reduce RDS on para walang headroom or walang masyadong dropout yung circuit. So yun po yung reason.
Okay. Okay, I guess that answers the question from Miss Mariela via the YouTube Live. We also have this pahabol na question from Mr. Jerome Reyes, Sir Doc Mikey, and it says, for newly board passers with high interest to semicon, especially to digital electronics, what would be a good stepping stone or career path for this field?
Okay, so I think if you are ganito po kasi no. If you are a digital designer, hindi na po kasi yung transistor level ang design. So I would suggest na you focus more on yung tinatawag nilang Verilog, or it's more of VHDL. So kinocode na lang siya, and then yung code itself is equivalent to a circuit. So you can try to master yung Verilog coding skill to develop your so-called, meron po kasing tinatawag na ASIC. That stands for Application Specific IC. And in fact po, if you're a good coder, you can actually develop yung microcontroller via the code. Kasi nowadays, I suppose wala na yung kung purely digital yung ginagawa, wala na siya yung i-build ko yung, let's say, gagawa ko na NOT gate, kukonect ko sa isang counter, hindi na ganun. Except if gagawa ka ng isang mixed signal circuit na, for example, for ADC or DAC or data converters. So, katulong story short, you need to strengthen your capability, especially on Verilog coding or VHDL. Kasi yan na yung digital niya. It's more of coding.
Okay, thank you for that, sir. Before we go to the last question, just a gentle reminder to our participants here in the Zoom and on YouTube Live, the link for the attendance questionnaire evaluation will be posted via the chat box as well as on YouTube Live. It will also be posted there. Likewise, via the YouTube Live, you can actually just scan the QR code that will be flashed on screen. So here's now the last question, Doc Mikey. It says, what do you think about gallium nitride, HEMT, replacing silicon in MOSFETs?
I think the main problem po of going towards gallium-based circuits is that medyo mahal po to implement. That's the main reason. For example po, no, gallium arsenide is very fast, but the problem is it's gonna be very expensive. So they're also trying to balance yung magiging cost nito when you try to deploy it in a large scale. So cost will be an issue.
Okay.
Ma'am,
Definitely. Yes?
ma'am, would like to answer yung BJT technology question, ma'am.
Okay, go ahead, sir.
I'm not sure kung... So, kay Mr. Senon, I would like to show you po this one. Hindi ko po kasi na-cover. Sayang. Maybe so for the next session, ma'am.
Okay.
Actually po, we are still using yung combination ng MOSFET and BJT. Ginagamit po siya for something called band gap reference. So dito po you see a BJT. Specifically, they use it, tinatawag po nila itong lateral BJT. So, dalawang BJT, tapos may resistor yung isa, pero Q1 will have a bigger area than Q2. And yung VBE po is CTAT siya, so bumababa yung VBE voltage with temperature, pero yung lumalabas na delta VBE is PTAT. So pag kinumbine yung PTAT na tumataas yung value with temperature with something na bumababa yung value with temperature, you create something called band gap. And marami na pong structure yan, and they are using bipolar, and yung transistor, yung op-amp is built using CMOS. So, buhay pa rin po yung bi-CMOS. And even po, just to add, meron din pong tinatawag na BCD. Hindi po siya yung alphabet. Ito naman po is bipolar. Tapos, ito yung CMOS and depletion. Kasi po, normally, pag sinabing CMOS, ito yung ginagawa, binibuild yung channel. Yung depletion naman po, nandun na yung channel. Dinideplete lang natin. Meron pa rin po yung BCD process. So may bi-CMOS pa rin to create yung mga trustable, dependable voltage reference na hindi tatabla ng temperature called band gap references. And meron pa rin po yung mga BCD processes that constitute bipolar, CMOS, yung mga enhancement type, and depletion. Ilan po, ma'am?
Okay, sir. Thank you for answering diligently all the questions, sir. And honest to goodness, sir, we are super loaded with information right now. And I guess parang need pa talaga tayo ng part 2 for this continuation on the digital side ng microelectronics, sir.
Yes, ma'am.
And we will be looking forward, sir, na ikaw pa rin yung magko-continue nung topic, sir. Okay.
Thank you, ma'am.
So, on this part of the day, we would like to acknowledge the presence of Dr. Angelo Beltran Jr. He was actually the one who referred Doc Mikey to us. And we are so blessed that even how time flies, it's already been the second time that Doc Mikey is our speaker here in Iecep-Socks chapter. Again, Doc Angelo, thank you so much for sharing to us, Doc Angelito. And we are looking forward more for more recommendations for probable speakers on a very informative topic. Also in attendance with us right now, we have the former governor of Iecep-Caraga, Engineer Jeffrey Deliosa. Likewise, the Oman governor, Engineer Jimmy Santos. And now we have our national president, Dr. Michelle D. Lawas, who is always with us, even from the time that the pandemic started. She is always supporting Iecep-Soccsksargen for all the activities, whether online or offline. So at this point, we would like to, since the Q&A portion is already done, we are so honored, Sir Mikey, Doc Mikey, for this. And with that, I would like to present to you the appreciation from the Soccsksargen chapter, and I would be reading the content of the certificates. It says, the Institute of Electronics Engineers of the Philippines Incorporated, Soccsksargen chapter, 4th webinar 2021. This certificate of appreciation is given to Engineer Angelito A. Silverio, PhD, for imparting his knowledge and expertise as a resource speaker during the Iecep-Soccsksargen chapter webinar with the topic Microelectronic Engineering from the Foundations and Beyond, given this 26th day of June 2021, signed by Engineer Tanya M. Osorio, MN ECE, our Iecep-Socs Governor. Okay.
Thank you, ma'am.
Before we end, we would like to request the participants kindly turn on your cameras. We will just have a short photo op to have a souvenir during this a very informative and nostalgic topic. I was actually even recalling my experience way back when I was still having my OJT at Maxim. So the wafer to complete package was already there. Okay. Is it okay now? So let's just wait for the committee to screenshot our presence here.
Okay. Ma'am Fel, I'll take the screenshot.
Yes po. Thank
Okay.
you.
Wait lang ha. Ayan, okay. There are 12 pages po kasi puno tayo ngayon.
Yes.
So, just hold your smile the entire time, okay? So, I'll start with the first page. Okay, one moment. Okay, page 1. Okay, page 1. Page 2. Page 3. Page 4. Yung smile natin, ano lang, diretso lang. Page 5. Okay, page 6. Page 7. Page 8. Page 9. Page 10. Page 11. And then last number, page 12. Ayan, so kompleto na. And thank you, Ma'am Fel.
Thank you. So thank you so much, Dr. Silverio. And we hate to say goodbye, but in all events, there's always a wrap-up. So to give us a closing remark, we have our enthusiastic and conscientious Vice Governor for Internal Affairs, Engineer Kimberly T. Gatorian, PECE, and actually she will be our next speaker for this first week of August for Iecep-Soccsksargen in cooperation with the Cordillera region. Caraga region, sorry. Okay, take it away, Ma'am Kim.
Hi, may hapon sa good afternoon everyone. Magandang hapon, naimbag nga malem. Mayat agat panapon, mayupay nga ulop, marhay nga hapon, buenas tarde. Mayong hapon, we are so overwhelmed with the very diverse attendance in today's webinar. We thank everyone for actively participating in this session. We also would especially express our gratitude to Doc Mikey, who shared his knowledge with us on microelectronics. We feel like going through our memory lane with this lecture. It's very detailed and very comprehensive. Memory lane for us, but for our students, I'm sure they appreciate this lecture as additional learnings in their microelectronic subject. So thank you, kids, for joining us today. Thank you to our Zoom participants. Unfortunately, we can only accommodate over about 300 of you. And still thank you for our YouTube participants. And yes, we read your comments as much as we can. And no, there is no need to comment for attendance monitoring, although your comments are highly appreciated. We also, of course, would like to thank Doc Beltran for introducing us to Doc Mikey. That simple introduction / recommendation has resulted to this very insightful and impressive webinar. Our gratitude to the Iecep National President, Doc Michelle Lawas, our advisor and inspiration. Salamat for being here with us. Thank you to all the chapter governors who are with us as well this afternoon. We are overwhelmed and no words could ever express our gratitude, but salamat. Ma'am Fel, back to you.
Okay, thank you for that, Ma'am Kim. And we are now gracing our last pasabog na mag-message sa atin on the group. We have our National President, Dr. Michelle Lawas. Ma'am. Okay. Ma'am, naka-mute ka po.
Not unmute.
Okay.
What happened? Okay, thank you.
Okay.
Okay, so thank you so much, Fel, Engineer Fel, no, for that introduction. So once again, I guess we have some National Board of Directors and Officers, no, who are present this afternoon, as well as our local and some of the foreign governors, no, who are also present, and especially to the officers of the Soccsksargen, headed by Engineer Tanya Mularto, our Governor of Soccsksargen, and of course with the officers and board of directors. Our guest speaker, I guess we have Dr. Angelito Silverio, no, for that microelectronics, and it is a wonderful topic, no, for all of us. Na even we are now migrating in the digital transformation, and we have this artificial intelligence and all that internet of thing, no, but still it's wonderful to hear about the basic of electronics and the basic of microelectronics and all of that. And of course to our distinguished guests, yung mga bisita natin coming from different chapters, as well as to all the panelists, no. So magandang hapon po sa inyong lahat. Actually, this is a very busy afternoon for all of us, since in the morning, then actually nag-attend pa tayo ng mga media convention with foreign chapter and this one. And I think for Soccsksargen, wow, we have an overwhelming attendance for this afternoon. And this is a good manifestation, no, na we are really, Iecep is really the driving force, or somehow we acknowledge that we are the front line in this time of a COVID era, no, and the COVID time. So with that, my respect to our speaker for this afternoon. Again, a very wonderful share, and we are able to linkage now with our mga magagaling na speakers natin, no, around the nation, from Engineer Beltran going down to Dr. Silverio now this time. So I think we could have another speakers, no, who are very powerful in terms of electronics and could somehow help us revitalize our membership and revitalize our interest towards electronics. So again, I would like to greet everyone who have joined us today as we take time to again venerate our engineers in Soccsksargen and other parts of the Philippines, Luzon, Visayas, and Mindanao, or even foreign. And it is indeed an honor to be part of this chapter, no? And of course, for the Soccsksargen chapter na on board talaga sila in this time of 2021 administration. And I am also very happy for the wonderful and a very supportive governor, as well as the Board of Justice and the Board of Directors, and even the members of Soccsksargen, no, for coming up for coming up an activity which is in support of the implementation of our Republic Act 9292. So again, I consider this as we have this indispensable roles, no, in the development. Again, even how high-tech we are in the empowering, in the migration of the digital transformation in the digital age, but somehow it is also nice to hear some of the basics of the foundation of our courses, the microelectronics, the electronics, or even telecommunication. Kasi nga parang lumilipad na yung ating era ngayon, but again, it is good to know that the growth of our nation in terms of electronics and being the claimant tayo no na we are the frontliner, then eventually we can contribute to the overall socio-economic, hopefully socio-economic, and as well as the political development of our country. So again, my congratulations very much as Soccsksargen for masyado kayong on board, masyado kayong aktibo, masyado kayong andyan sa administration natin, and hopefully on the coming years and on the coming journey ng Iecep, we will be together, and together we can do so much. And with that, again, congratulations and good day, everyone.
Okay, thank you for that, Doc Michelle Lawas. Again, we are so grateful on behalf of Iecep-Soccsksargen. We are so grateful that the strong 295 participants are still tuning with us right now. So before you go, I would like still to invite you for the upcoming Soccsksargen chapter, a tie-up between Soccsksargen and CAR region for a webinar collaboration that would be entitled Instrumentation and Automation in the Manufacturing Industry, which will be delivered to us by a PECE engineer Kimberly P. Gaturian, which is also right now our Vice Governor for Internal Affairs. So if there are no more questions, no more other, let us all pray for a closing prayer. So let us put ourselves in the presence of the Lord. Thank you, Lord God, for gracing us your presence this afternoon. We are still thankful that you are keeping us safe all the time, despite this pandemic. We will always be grateful to you, O Lord, and we will give you all of the glory back. In the mighty name of Jesus, we pray. Amen. Thank you for that. Have a nice day. Bye-bye.
Thank you, everyone. Bye.
See you in August.